but that's going to be the link. There will be a break at 3 p.m. If at 3:10 you see that I'm still going on like a madman through the slides, then feel free to interrupt me and remind me that you are entitled to a break. At lunch, those with dietary needs should let the server know, but lunch was before, so I guess that's not necessary anymore. We have placed as much power as we could afford. Please share the outlets. Outlets could be in your row, or the row behind you, or the row in front of you, just like exits in planes. All right, so this is deploying and scaling application with Docker, Swarm, and a tiny bit of Python magic. So if you got into the wrong tutorial, now is the time to sneak out. Normally, on your table, you should have a little piece of paper like this. If you don't have this little piece of paper, then raise your hand and somebody will give you one. This little piece of paper has a list of IP addresses and credentials to connect to a cluster of virtual machines. If you were in the Intro to Docker tutorial this morning, we have a different set of virtual machines. This morning, we just dealt with one machine at a time. This afternoon, we have a whole cluster of 5 machines to play with. If you go to container.training, just like this morning, you will find a nice little menu like this. And I'm going to, again, show that this is the full extent of my HTML abilities. And so if you click on the Advanced Docker and Orchestration HTML slides link, then you will get the slides that we are going to use right now. I also invite you to have a tab open on Join the Conversation on Gitter. Gitter is a small instant messaging platform, a little bit like Slack, except that if you already have a GitHub account, it will just take you a couple of clicks to join, and that will give you the opportunity to ask questions, give feedback live during the session. Obviously, I will not be able to simultaneously present and check this window for questions and answer the questions. But AJ, who is here in the back, also monitors that channel. And so if you have questions, like you feel asking something, but if either you're shy or not sure if you should interrupt me, well, first, don't be shy. It's totally okay to interrupt me. But even if you don't want to, then you can type your questions there, and then we can help. Right. So I did the announcements. We covered this, so let's get started. So the tutorial will run until, is it really 5 p.m., something like, or 4:20, can't remember. There will be a break from 3 to 3:30. This will go pretty fast because there is a lot of material, I know, and so I decided to make the bet of going maybe a little bit too fast rather than a little bit too slow, because the whole content is available online for free. So if there is stuff that you want to do on your own after, you're welcome to. The VMs that you have for the tutorial will be available until probably late tonight. And the content will continue to be available. So all the slides, all the code samples, all the scripts that we use here are public and available. And after each of those tutorials, I put a tag on the repo so that if in a few months you want to see, okay, what's up, what has changed, you can easily make a diff to see what has changed in the land of Docker, Swarm, and orchestration. All right, so this is the rough outline for today. The first part, so we'll cover static orchestration and deployment. So we'll talk about the pre-requirements, the VM environment. I will present the sample application that we will use during the whole tutorial. We will run that sample application. We will identify some bottlenecks, and we will see how to scale it out. Then we will connect containers running across multiple hosts and abstract remote services with ambassadors. Then we will move to the land of dynamic orchestration. We will deploy Swarm. We will use a console distributed key value store to implement overlay networks on top of Swarm. We will see how to do resource allocation, multi-host networking, how to build images when running on a Swarm cluster. We will deploy a local registry and see how to scale our application on this cluster. Then in the third part, it will be about Docker for ops. So we'll see how to do logging. We will set up an ELK, Elasticsearch, Logstash, Kibana cluster and send the logs of our containers to this cluster. We will see how to do network traffic analysis, backups. We'll see a few interesting patterns when administering clusters and talk about security upgrades. There is a fourth part that we will not cover today, but that I decided to keep in the materials because I give multiple versions of this tutorial. There is like the full day version and the half day version. So in the half day version, I remove a few things. But many people have questions about high availability. There is no way that I can fit the whole thing in 3 hours, or I could if I were to go so fast that everybody would be like, this is going too fast. And I'm sure a lot of you will already think that this is going too fast, so I didn't want to take the risk to go even faster. But I decided to keep the last part on high availability in the materials so that you can see what to do if it's something that you want to learn more about. All right, let's get started. So part one, let's get warmed up. So pre-requirements, you should have a computer, check. With network connectivity, we're going to use the local Wi-Fi and an SSH client. I see that most of you have MacBooks, so you already have an SSH client. For those of you on Windows, I hope you got the email message and information about the requirements telling you to have an SSH client. If you don't have one, it's still time to get one using either PuTTY, Git Bash, or MobaXterm, the thing of your choice. You need some basic Docker knowledge, but if you know how to start a container with Docker run, if you know how to write a simple Docker file and build it, you will probably be fine, because I'm going to try to not leverage on this basic knowledge too much. I'm going to use Compose a lot and to introduce Compose as we use it so that you can learn whatever is your current Docker knowledge. A few things that are nice to have. So a GitHub account, just if you want to fork the repo that we're going to use, or if you want to join Gitter. It's nice to have a Docker Hub account, but it's not strictly necessary either. The whole tutorial is built to be hands-on. So there is some educational theory about like some people learn better if they have some kind of theoric explanation. This is how things work. Some people learn by watching someone do things. Some people learn by doing things themselves. And so I try to mix a little bit of all that. So I will talk a lot. Then I will also go to the terminal and do stuff in the terminal. And so if you want to do stuff by yourself, there are a bunch of gray rectangles in the content with the exercise and this little squiggly thing here, which is supposed to be a keyboard. That stuff is that shows the part that you are supposed to do if you want to follow along. It's been designed so that if you go over the material later and you just want to do all the hands-on part, you should be able to get all the commands in those gray rectangles and copy-paste them to the terminal, and everything should work, hopefully. So the first thing that we're going to do is to go to container.training to view the slide so that you can have the slide on the side, because most of the commands will be easy to type, but there will be a few commands that I recommend that you copy-paste, because it will be like 5 or 6 lines and a little bit of shell scriptery. And so in that case, it will be easier for you to just copy-paste from the slides. And I also, if you're so inclined, I would advise that you join the Gitter chat room so that you can, again, ask questions or give feedback or complain or praise or whatever you want. That's really useful for us to improve the tutorial as well. So let's talk about those VMs that you have. So reminder for those of you who just joined us, you should have a little piece of paper like that. If you don't have it, just raise your hand so that someone can give it to you. No, everybody has it? Great. So the first thing that we will do is that we will log into those VMs and check that they work fine, because those are cloud VMs that were just deployed. So, I'm going to SSH. Is this readable from the last row? Yep, great. So SSH docker and I put the IP address of my Node 1 VM. Please put the IP address of your Node 1 VM, not mine. Otherwise, we will end up stepping on each other's toes on these VMs, and that's going to be inconvenient. All right. Am I the only one with network issues, or? I think I'm already on the 5 gig network, but oh, that was just a transient thing. All right, and so the first thing that I'm gonna do, I'm going to do Docker version to check that Docker is indeed installed on this machine, okay. And then I'm going to do SSH node 2, and we have SSH keys that have been preloaded on those machines so that we can hop from one machine to the other without having to type the password each time. So for instance, if I'm on node 1, I can do SSH node 2 directly without putting the password and vice versa. And there are aliases for the 5 nodes, node 1, 2, 3, 4, 5. And if you wonder how that works, it's like plain old aliases in /etc/hosts, so nothing really magic here. I do apologize, the network is being a little bit slow, but it will hopefully get a little bit better. And if you might be thinking, oh, it would be better if we had like local machines to do all that, the answer is hell no, because when the time to install stuff on the VMs will come, we will have to pull packages, and then like 50-ish of us pulling packages at the same time on 5 VMs, that's going to just not work at all. So even if SSH sometimes is a little bit slow and sluggish, it's still way better than having to really pull down those packages locally, trust me. All right, so can you raise your hand if you were able to log into node 1 and then from there log into node 2? Now can you raise your hand if that didn't work so that we can help you? Oh, 1 person here, 2, 3. So I think 1 person on the back might be missing the little paper, and AJ is going to help you to catch up with that. So during the whole workshop, we will interact mostly with node 1. There will be a couple of exceptions where we will do stuff on the other nodes over SSH, but the rest of the time, everything will be on node 1. We will get the code only on node 1. We will log only on node 1, and we will run containers on the other nodes, but we will not use SSH for that. We will use a different method. Okay. Once in a while, I will say like open a new terminal or open a new window. That just means you need to get another shell inside the VM. So depending on what workflow you prefer, you could like pop up a new window and SSH on the machine, or if you like, you can use something like screen and tmux. So you just log once into the VM and then you just screen and tmux. I'm personally a big fan of tmux, so I've put this cheat sheet here to remind me of the most common keystrokes. However, if you have never used tmux before, I don't recommend that you start now because that's going to be a little bit bumpy, but check it out after, it's a great tool. So on those VMs, we have brand new versions of everything. I mean, everything in the Docker platform. So we have Engine 1.11, Compose 1.7, Swarm 1.2, and Machine 0.6. Machine is the only exception here. The latest version of Machine is 0.7. We use 0.6 for reasons that I will explain a little bit later when we come to cluster deployment. The application that we will use during the tutorial, so it's in this repo over here. So I'm going to open a new tab and go to the link here. So it's Orchestration Workshop. And the app is in the Docker Coins directory here. And this app has a compose file. So the compose file describes the application. Maybe I could unzoom a little bit. So in this compose file, I see that we have 5 services: RNG, Hasher, WebUI, Redis, Worker. Redis is just using the Redis image straight from the Docker Hub. So that one is really easy. It's like pull the image from the hub and run it. The 4 others, though, are using Docker files that are in subdirectories in the repo. Like you can see, RNG is built using the RNG directory, Hasher is built using the Hasher directory, and so on and so on. I tend to be not very original when picking those kind of names, and I think it's a good idea because service X is in directory X, and it doesn't get any simpler than that. So if we go into those directories, each time we'll find a Docker file that describes how to build this specific component. So for instance, for the hasher one, it says to use the Ruby image. It installs a few gems, and then it copies a little bit of Ruby code in it. Then if we go to another one, for instance, if we go to worker, the Docker file is using the Python image and has some Python code, and so on and so on. Each service, each container is using a different language and framework. Okay, so if you already have used Compose before, there is one thing that you might want to know about here, is that in the Compose file, there is a version tag on top, and if you've used Compose before, maybe you have never seen that. If you used Compose v1, in the Compose v1 file, you only have the content of the services section. The Compose v2 format puts all the services under a dedicated services section and allows you to define extra entities like networks and volumes, but you can safely ignore that for now. And let me try to pop that out or have a new, yeah, that will be better. No, that won't work either. Okay. Okay. So with the Compose v2, all my containers will be placed on a custom network, and they will be able to reach each other using container names. So this means, for instance, if we look at the code of the worker service, worker.py, we see that when it wants to connect to the Redis service, it connects to Redis. It doesn't connect to 192.168.1.1 or to some domain name. It connects to Redis, and then Docker, when it starts all those containers, makes sure that the Redis container will be on a specific address IP, and the Redis name will map to that address IP, to that IP address. So when the worker tries to resolve Redis, it gives the IP address of the Redis container. Likewise, when it tries to resolve the names RNG and hasher, it will get the IP addresses of RNG and hasher. So it makes the code kind of simpler because you don't need to do service discovery, you don't need to have a config file to indicate those are the addresses of my different dependencies. You can just use those names, and Docker will expose a little DNS server to automatically map those names to the right containers. So now what is this application that we're going to use? It's a Docker coin miner. Docker coin is not an actual cryptocurrency. It looks a little bit like Bitcoin because it's hashing stuff and using CPU cycles and memory and resources and contributing to global warming, but it's not an actual cryptocurrency. It's just like a demo app for educational purposes. So how does it work? We have a worker that does an infinite loop, and in this infinite loop, the worker will contact the RNG service. RNG stands for random number generator. So it will get a little bit of random data, then it will post that data to the hasher service, and the hasher service will compute the SHA digest of that little bit of data. And then after that, the worker will just increment a counter in Redis and repeat. So get random data, hash random data by posting it to the other service, increment counter, and repeat and repeat and repeat. So it doesn't save any practical purpose, it's purely educational, but it involves a few microservices, RNG, hasher, the worker. There is Redis as a data store that just stores this counter, nothing else. And there is a web UI which connects to Redis and just displays a graph showing how fast we are doing this infinite loop. So we're going to get the source code on node 1 by cloning the repo. I'm going to do git clone. And I'm going to trust that my connection is still up. Yep. Git / github.com and github.com /jpetazzo /orchestration workshop. Then I'm going into orchestration workshop, and Here, this is the whole repo, but the application that we are going to use is in Docker coins. The other directories, like the slides, are in the www directory. The prepare VMs directory contains the scripts that we use to start those virtual machines. So if you want to redo the tutorial by yourself, or if you want to deliver that tutorial to other people, you can start the VMs with the scripts contained here. And there are a bunch of other directories with tools and other things that we will use during the tutorial. And so in the Docker coins directory, this is my application and the whole source code. So the first thing that we are going to do is that we're going to start this application, and we're just going to execute docker compose up. So when we do docker compose up, compose will pass the docker compose YAML file, and it's like, oh, okay, so you have a bunch of containers that I should build. So for instance, it says building worker. So it goes to the worker directory. It says, okay, there is a Docker file. So I'm going to build the container image from that Docker file. And then it's going to hasher, which is based on Ruby. So you can see it like pulling the base images and then building the Docker file. Those Docker files in turn will download a bunch of dependencies and build each service one by one. The first build takes like a couple of minutes, but all subsequent builds are super fast thanks to the caching mechanism in Docker. Like even if I change the code and I build again, it will takes maybe a couple of seconds to rebuild the whole app. The whole app, sorry. So microservices style, we have some Python stuff, we have some Ruby stuff, and now it's going to build the web UI, which is in Node. I don't necessarily recommend that you use 3 different languages in your stack, but for demo purposes, that works well. All right, and now my app is up and running. So what we see here, I'm going to zoom a little bit. I will probably constantly kind of zoom and unzoom because sometimes I want everything to fit on screen. If you're on the last row or even not on the last row and you can't read the screen, just like gesture to me and remind me to zoom in something. So that's the logs of the application. And so we can see this whole loop. I'm going to pause that with Control S. I can see RNG says, yep, we got some random data. Then hasher says, yep, we got posted some data. And then it's again RNG and hasher and RNG and hasher. And once in a while, worker tells us, I've done 4 units of work so far, and now I'm updating the counter. Because yes, in fact, the worker is not updating the counter after each loop, but just once per second. And every second, it's like, how many units of work did we do so far? That much? Okay, fine. Increment the Redis counter by that much. And so if you pause the logs with Control S, you can resume with Control Q. That's not Docker specific, by the way. It's work with any terminal stuff. You can Control S, Control Q to scroll lock and scroll unlock. All right, that's great, but that's very verbose and not extremely useful. So I'm going to do Control C. And Compose will be like, okay, you want to stop that app? Fine, let's do that. And once the app is stopped, I'm going to run it again, but in the background with Docker Compose up -d, like detached or demonize, exactly like Docker run -d. And that's going to restart the application, but in the background. Okay. So now, yes? Yeah, just to be clear, that's all running on Node 1. At this point, we are only running Node 1. I hope I will make it clear enough when we start running on the other nodes, yeah. So now that my app is running, I can do Docker Compose PS, and that works exactly like Docker PS, except it shows me only the containers of my application and in a slightly different format. Here, what I want to see is the web UI. So it tells me web UI, port 8000 on my host is mapped to port 80 in the container. So I'm going to access my cluster node. So I'm putting the IP address of my cluster node on port 8000. And I will get the web UI. And the web UI shows a graph like this. If you look on the left, you will see a scale, so that indicating the speed. And at the first glance, it looks like we're doing 4 Docker coins per second. In fact, if we want to be accurate, we're only doing 3.3. This is because we're doing 4440, 4440, 4440, and so on and so on. This is because the worker doesn't exactly report the speed every second. It reports it up to once per second. So it will mine 4 Docker coins or do 4 loops, and then it's like, oh, it's been more than 1 second since the last update, and it's going to update the counter. But it takes a little bit more than 1 second for the whole thing to happen, which means that when you are looking on the counter, the counter doesn't do 0, 1, 2, 3, 4, 5, 6. It's doing 0, 0, 0, 4, 4, 4, and then it's doing, scratch that, it's doing 0, 4, 8, 12, 12 again, 16, 20, 24, 24 again, and so on and so on. It increments by steps of 4 units, and sometimes it doesn't increment between two times when you look at it, which is why on the graph we have this kind of comb-shaped thing where it looks like we're doing 4 and then 0, and 4 and then 0, and so on and so on. Okay. So the whole goal during the tutorial will be to scale that up so that this graph goes as high as possible. Now that the app is running in the background, we can inspect logs with Docker Compose logs. So if you do that, it will just dump all the logs since the application has been started, which is a lot of logs and not extremely helpful. But we can use the same flags as for the Docker logs command. So you can do Docker Compose logs --tail 1 --follow, which means show me the last line of log from each container and then continue to stream those logs. So if I do that, what I get is slightly more useful because at least I don't get flooded by all those logs. Okay. Connecting to the web UI, perfect. So now, we want to scale up. So first, we're going to do a little assessment of what kind of resources are we using. Why are we doing this between 3 and 4 loops per second? Why aren't we going faster? Do we need more CPU? Do we need more RAM? Are we I/O bound? So we are going to check with a few classic Unix tools. So I'm going to run top, and top will tell me that I have a Python process running here, but it's using 1% of CPU. I see a Ruby process, and I see Docker itself, but I can see that my machine is 99% idle, 98% idle. This machine is essentially doing absolutely nothing. So I'm going to use another slightly more sophisticated tool, vmstat. I do vmstat 1, so it means refresh that display every second, and it's telling me that I have roughly 0 process in the run queue at a given time. I have plenty of memory available. Swap SISO, it's at 0, it means I'm not swapping at all. BIBO is block in, block out, so how much am I reading or writing from disks? And I'm reading nothing, and I'm writing very little. So we are not I/O bound either. So it looks like the machine has plenty of resources available, and we should just try to scale and see what happens. So that's what we're going to do. So Compose has built-in scaling. There is a command that lets you create more containers like one of the containers of your stack, Docker Compose scale. We're going to try that. So since we have the worker that does this infinite loop, we're going to have multiple workers in parallel. And if we're lucky enough, that should just work, because now we have multiple workers doing the whole get random data, post the data, increment the counter, and again and again. So Docker Compose, scale, worker equal to. And as I do that, I go to the web UI, and I have a little spike, and after it stabilizes to roughly 2 times what I had before. Before I was at 4-ish, and now I'm at 8-ish. So it looks like it worked. Let's see if we can go farther. Going to do Docker Compose scale worker equal 3. And as I do that, yep, it's going higher. Okay, so it looks like we should be able to do like Docker Compose scale worker equal 1,000 and call it a day. We won't try 1,000 because that's a lot of containers, but let's try with 10. And as we scale to 10 workers, we could expect maybe to see like between 30 and 40 on the graph, but no, the graph will kind of be capped at 10 hashes per second, and it won't really go higher than that. There are little spikes where it goes higher, but it's just the way we measure speed, which is not really accurate. It's like the speed is measured client-side by some JavaScript code written by truly yours, so it shouldn't be trusted for anything. But it's doing like 10 hashes per second. And I can add more workers. It will not go higher than that. If you don't trust me, I'm going to put like 15 workers, and that's not going to budge a single notch. All right, so maybe now I'm using peak capacity. Maybe I'm maxing out my CPUs or my memory or my whatevers. So let's look at that. Once again, I use stop, and I look at the output, and now I have a bunch of Python processes because I have a bunch of workers, so that makes sense. I still have my Ruby process, that's the hasher service, and I have a few more like Docker, containerd, shim, something processes that show up, and I still have Docker itself. But more importantly, if you look on top, I have 94% of idle CPU time. So I have plenty of available CPU cycles. If I do vmstat1 again, it will confirm that I still have tons of memory available. It will also tell me that I'm doing a little bit more of block out of disk writes. Like you could wonder, like earlier, BO was like 40, 50. Now it's like 150 once in a while. This is because my containers are writing logs, and those logs are being captured by Docker, and Docker then writes them to disk. And so once in a while, those disks are being actually written to, like it were written in memory and then it's flushed to disk. So every 5 seconds, the pdflush kernel thread is committing those writes to disk, and that's why we have this little burst in writes. But that's nothing. It's really like the disks are not doing anything. So we still have plenty of resources available. So let's try to find out how we could go higher than that. So something is slowing us down. If this were like a real application, we would probably be using something like statsd or Neuralink or Datadog that would give us some insight about like the critical path in the code. But this is just a demo app I wrote a while ago, and I wanted the code to be super simple. So we will have to use state-of-the-art HTTP performance analysis tools like Apache Bench or HTTPing. Specifically, we're going to try HTTPing. HTTPing is just like ping, except instead of sending an ICMP packet and getting the reply back, it sends an HTTP request, and it checks how long it took for that HTTP request to come back. So I'm going to do HTTPing, localhost on port 8000, localhost 8001, that's the RNG service. And the RNG service replies in 1200 milliseconds, so that's a little bit more than 1 second. That's slow, especially for a service that's running locally. Let's compare with the other service, Hasher, running on port 8002, and that one replies in 1 millisecond, which is closer to what we would expect. So it looks like RNG is kind of in trouble. And to confirm that, I'm going to scale back, so docker compose scale worker equal 1, because I want to see if I remove some workers, then will RNG be kind of more comfortable serving my requests? And now I do again like HTTPing localhost 8001, and fair enough, we are down to 1 millisecond of response time with once in a while a little 60 millisecond thing. And here, if we were to increase the load, like adding containers one by one, we would see that increase and increase and increase. So RNG seems to be the culprit, the thing preventing us from scaling up. We're going to draw hasty, wrong conclusions. I'm going to say, oh yeah, I know this. We're using a random generator, so we're getting entropy from /dev/random, and we probably don't have enough entropy. We should like scale out to multiple machines, so that way we can have more entropy, and that will solve the problem. This is completely wrong. I mean, the problem is not the /dev/random entropy pool. But we're going to pretend that it's the case because it gives us a nice opportunity, a nice excuse to scale out to multiple nodes. So we're going to scale out. And we're going to run that whole application stack on multiple nodes. So we need to connect containers across multiple hosts because so far we have everything on one machine. We want to have things on multiple machines. How will our containers talk to each other? So the only thing that we need to talk to, like the only thing that needs to be centralized is the Redis container. All the other components can remain like in their own little island. I just need to make sure that all my workers talk to a central Redis service. Because if I just make multiple copies of my stack, I get like multiple worker and hasher and RNG and Redis, and I have multiple counters being incremented. But what I want is one central Redis, and I want to be able to create workers on different machines and everything contributing to my Docker point mining pool on this central Redis service. Another thing is that, so what I could do is, hey, let's spin up a Redis service somewhere, and then let's change the code so that instead of connecting to Redis, I'm connecting to this IP address on this port. But new rule, we are not allowed to change the code. So we have to find a way to connect to this central Redis service without changing our application code. And what we're going to do is that we're going to abstract the remote service with an ambassador. And this is what this is going to look like. This was our old application stack. So I have all my 5 containers on the same machine. What we're going to do is that we will have Redis running somewhere. Doesn't matter exactly where. And this Redis will be reachable from outside on a public IP address and port. Then we are going to have a copy of our stack, but where Redis is replaced by what we call an ambassador. An ambassador is a proxy or load balancer or traffic director, you can call that whatever you like, and it pretends that it's Redis, but what it does is just accepting connections on the default port for Redis and relaying the traffic to the actual Redis service. So my code will connect to Redis. Redis will not be the actual Redis service. It will be the ambassador listening on the default port for Redis, so 6379, and this will relay the connection to the actual Redis service running somewhere else. And then I will just create more copies of that stack so that on each node, my code is connecting to a Redis ambassador, and the Redis ambassador then relays the traffic to the actual Redis service. And I can start as many copies of my stack as I want. So the first step is that we're going to start the Redis container. I'm going to do docker run, -d because I want to run it in the background, -P, which means publish all the ports for that Redis service, make it publicly reachable, -- name my Redis because I like giving names to my containers, and Redis. All right, now if I do docker ps, in the output I see here I have a Redis container, and the port 6379 of that Redis container has been published on 32768 on my machine. Okay. Next step, I have to put this ambassador. So it's a little bit like a TCP load balancer, but with only one backend. Like you connect to it, and it always sends the connections to this Redis service. We are going to use the jpetazzo/hamba. So it's a little image I wrote so that we don't have to learn about how to write a load balancer configuration file. What it does is that it parses its command line, and then using that command line information, it generates an HAProxy configuration file, and it starts a HAProxy. The command line should have the port on which you want to serve traffic. So for instance, the little examples here are using HTTP. So it's like listening on port 80 and load balancing traffic on backends www1 on port 1234 and www2 on port 2345. You can specify the backends either with host colon port or host space port. It recognizes both, so it's convenient. Here in our stack, we are going to listen on port 6379, and we are going to specify only one backend, our Redis service. So we are going to edit the Docker Compose YAML file, and in the Docker Compose YAML file, we will replace the Redis service with this ambassador. I'm going to use VI, but you're welcome to use another editor of your choice. So Docker Compose YAML file, I'm going to Redis, and image, I'm going to put jpetazzo/hamba, and then command, so that's the command line to pass to this container. Listen to 6379, connect to the IP address of node 1, so I'm going to put the IP address of my node 1 here, but you should make sure that you put the IP address of your node 1, otherwise your containers are going to end up connecting to my Redis, which is not a big deal, except that when you look at your graph, it will be at 0, and mine will just go higher, which is not a big deal, but it might be surprising. And then the port on which my Redis container is listening, so that's 32768. That's the port that we saw earlier when we did Docker PS. And that's pretty much all I need. I'm going to write this file and exit. For each time we are going to update the Docker Compose YAML file, I have a shortcut file. So in that case, it's called Docker Compose YAML-ambassador. So if at some point, like at this point, it's still pretty easy, but at some point, if you're lost in the change and you're like, okay, I need to catch up on what we are right now, you can use the shortcut file to find the YAML file in the right state. There are still a few changes to do. Like in that case, you need to put the IP address of your node 1 and the right port number, but that can help you to catch up. And we are going to start the stack on the first machine. So I'm just going to do docker compose up-d. My stack is already running, but compose will be smart, and it will look, oh, so you changed the definition for the Redis service. Before, it was like an actual Redis container, and now instead it's going to be the jpetazzo/hamba container. So we're going to replace this container with a new container. So I do that, it's going to pull the jpetazzo/hamba image, and then it starts everything. And if I go to the web UI now, I should see, yeah, it's still working because I still have a Redis service. What just happened is that the previous connection was broken, and now it's talking to the new Redis service. Okay. So now we need to deploy the stack on the other nodes. And for that, we could use SSH on node 2 and git clone and change the compose file, or we could copy the compose file on the whole cluster, but that wouldn't be very convenient. Instead, we are going to stay on node 1, and from node 1, we are going to control the other nodes using the Docker API. The clusters that you have here have been set up to accept Docker API requests on port 55555 without authentication. Sorry. This is not secure and you should not do it, but for educational purposes, we open those ports so that we don't have to deal with security and certificates yet. We will do that later, don't worry. So how do we tell our Docker tools to speak to other nodes? We just set one environment variable, Docker host, and all well-behaved tools in the Docker ecosystem will follow that environment variable. The Docker CLI, Docker Compose will follow that. Other tools will as well. So I'm going to do here like Docker PS. So when I do Docker PS, I see like my Redis container, and I see the containers of my stack. And if I do now export Docker host equal TCP : node 2 : 55555. Now if I do Docker PS, I see nothing because I'm now talking to node 2, and node 2 is completely blank. We haven't started any container on it yet. So I'm going to start container by doing Docker Compose up-d. So Docker Compose will be like, oh, it looks like you don't have any container here. I need to build everything and start those containers. So here, if you're kind of going a little bit ahead of me, You might think, wait a minute, I thought the whole idea was to build my images once and then run anywhere. Why am I rebuilding all my containers? You're totally right, that's not optimal, and we will soon see how we can build once and then deploy the same image everywhere. But for now, we are going to use that because it's really super simple. So that's going to take like a couple of minutes to build everything again. And once this will be built, I will do the same thing on nodes 3, 4, and 5, but I will use some shell scripting so that it's faster. So here we have a couple of minutes while it's building on all that. So that's a good checkpoint, like if you have questions. Nope, everybody is still kind of in this post-lunch thing. We need more caffeine. All right, so now the stack is running on node 2, and if I look in my web UI, I see like a bump, and I'm now going at like 8-ish Docker coins per second. So it's exactly like when I scaled to 2 workers, except that now I have 2 copies of the stack on 2 machines, and I'm going to start more copies on the stack, but scripting things in parallel. So with this little snippet here, so for n in 3, 4, 5, do docker host equal tcp / node $n : 55555, docker compose up -d ampersand don't wait. Whoops, I forgot the semicolon. Okay, so now I'm doing the whole build and start the stack on nodes 3, 4, and 5, but in parallel. Still no question during this 2 minutes opportunity when we have to look at this? Oh, sorry.
So how do you tell Docker to accept on 5555?
How do I tell Docker to accept on 55555? It is the way that we deployed those VMs. We added a little configuration option so that Docker would accept connections on 55555. I can show the configuration, I think. Give me just... all right. So in that case, that's going to be, I think, let's see if I can remember libsystemd. So the exact configuration will depend on what you use. Like in the case of systemd, you have to change the systemd unit. So in that case, it's like Docker daemon, and it's this -h option where we say accept connection on TCP 0000:55555. Yeah. And we will see like a little bit later how to do that in a better way, like especially to have TLS certificates for security. All right. So I've deployed my stack on the 3 other nodes, and if I go to the web UI, I have more Docker coins. So I'm like, okay, well, but the next step is that now that my whole stack is running on those 5 nodes, I can scale up on all 5 nodes really easily, really quickly, and I'm going to do just that. So I'm going to do for n in 1, 2, 3, 4, 5, do docker host equal tcp : / node $n : 55555, docker compose scale worker equal 10, done. So I'm scaling on the first node, and then on the second node, and then on the third node, on the fourth node, on the fifth node, and each time we can see like the graph going up and up and up until we reach 50-ish hashes per second. On one node, we had a peak of 10 per second, so on 5 nodes, we had 50 per second, more or less. That's consistent. All right, so that's satisfying. Everything worked more or less as expected. So now what happens if we try to access the web UI on another node? So I'm going to put the IP address of another of my nodes here, any other node, doesn't matter. And I will get, and port 8000 for the web UI, I will get cannot get index.html. What's going on here? This is happening because we have volumes for the web UI. If we look in the compose file here, for the web UI, we have volumes ./webui/files:/files. Why does this mean? It means that when we are starting the container, we are telling Compose, hey, I want to map directory ./webui/files in the host to /files in the container. ./webui/files translates to /home/docker /orchestration workshop /dockercoin /webui/files. On node 1, this directory exists because we checked out the code on node 1. But on node 2, 3, 4, 5, we did not check out the code, so this directory is empty. So on nodes 2, 3, 4, 5, when I try to access the web UI, the static assets don't exist, and Node is telling me can't access index.html. If I want to fix that, it's actually really easy. You just have to comment out those 2 lines to basically tell Compose, don't overwrite the files in the container with the local files. Those 2 lines are useful for development purposes because they let you make changes in the static assets, so the HTML and CSS and JavaScript of the web UI, without having to rebuild and restart the container each time. But once you are out of development, you should just remove that and let the container use the files that are in the container. Okay, so we are going to stop the application before we move to the next chapter. And for that, we are going to use Docker Compose down. And there again, I'm going to use that in a loop. So I'm going to do for n in sec15, do docker host equal tcp://n:5555 docker compose down ampersand down and wait. So I'm stopping my 15-ish containers times 5 hosts all in parallel at the same time, and so like 10 seconds later, my whole app will be gone. And if I go like to the web front end right now, it doesn't even show 0. Like the web UI doesn't exist anymore. So what we have now is this HTML5 app, which is kind of trying to access to the counter in Redis, but it just doesn't work because there is no, the front end is gone. So now if I check like Docker PS, I'm currently talking to node 2. And so on node 2, all my containers are gone. If I unset Docker host, so now I'm going to talk to the local Docker engine again. If I do Docker PS, then I just have the my Redis container that is still running because this container was started independently of Compose. So when I do Docker Compose down, Docker Compose is not touching this container. All right. And we're going to remove that container as well. So docker rm-f myredis. rm-f with Docker means remove the container even if it's running. If it's running, it's going to kill it first. All right. So a few words about ambassadors before we move to the next chapter. Ambassador is a design pattern. It's not using HAProxy to send traffic. It's not jpetazzo/hamba. jpetazzo/hamba is just one example of how to implement ambassadors. There are many ways to do that. And here I have a few slides like with escalating more and more complicated ways to implement ambassadors. Like you can have single tier where you have like you have one script that will configure all your load balancers. You can have 2-tier ambassador deployment where you say, okay, instead of having to push the big button that runs the script that configures the load balancers, I want to have an automated system that listens to Docker events because the Docker API is exposing events, and each time something happens, then I want to dynamically add, remove, update the backends for my load balancers. Then we have the 3-tier ambassador system, which kicks that a notch farther, where instead of directly listening to the stream of events and updating the load balancers, in the middle, we put a configuration database, for instance, a highly available key value store like console, etcd, or zookeeper, and we have something listening to events and registering the containers in the key value store, and then we have another or even multiple other programs reading from the key value store and updating the load balancers. That lets you decouple the complexity so that, for instance, you can have this one thing that puts all the containers in the key value store, and then you can have something in charge of MySQL replicas management, something in charge of this specific web app load balancing that is using like a session stickiness, session affinity with cookie stickiness, this other web app which is using a different load balancing policy with a different load balancer, and so on and so on. There is another mechanism to achieve communication between containers, overlay networks, and we're going to see that like within the next hour. And so that was static orchestration. We are going to move to dynamic orchestration. Let's see on the timing. Okay, good. So dynamic orchestration, what's the difference between static and dynamic orchestration? With static orchestration, we decided what would go where. We say, okay, this is my whole stack, and I'm just cloning that stack multiple times on different machines. With dynamic orchestration, I just want to throw containers at my system, at my platform, and I want the system to automatically dispatch those containers around, following, for instance, rules about memory usage or CPU usage. Like I have a machine with 10 gigs of RAM, and I have containers using 1 gig of RAM, so it will automatically stack up to 10 of them, but no more. The advantage of dynamic orchestration is that you don't have to worry about like those specifics of what goes where. So at first, it looks like, do we really need dynamic orchestration? I mean, I can just start those things and that should work. I know that I can put those containers on those machines. It's true in the beginning. Because in the beginning, you have like this small 5 nodes cluster, and it's pretty easy to remember what runs where and where. Okay, on node 2, I've put like the production Postgres database, so I should not put anything else that is I/O intensive. On node 5, I have this image conversion thing, so it's CPU intensive, but it's okay for the other resources. Good. Now, if you have 100 machines and you have thousands of containers, good luck remembering which ones are currently under load and what should go where. So that's where you need dynamic orchestration, where you will just say, this container needs tons of memory, this container needs I/O, this container needs CPU, and the orchestrator, the scheduling system, will automatically put the containers on the right place. All right, so and for that, we're going to use Swarm. So Swarm in theory and in practice, so in theory, like the principle of Swarm is that it takes a bunch of Docker engines together and it makes them appear as a single Docker engine. So for instance, when you do Docker PS, you see all the containers on all your engines. If you do Docker run, it will automatically pick one of the engines and start the container there. So for you, it will be, I would say, very transparent, not absolutely transparent, but very transparent. It will really look and feel like as if you had one big Docker engine, but in fact, it's a cluster. To achieve that, it's going to expose itself as a little process that talks the Docker API front and back. So you talk to Swarm with the Docker API, which means you can use the Docker CLI, you can use the Docker Compose, you can use any program you've wrote previously that is using the Docker API, and you can talk to Swarm instead of talking to a single engine, and that will work. And then in turn, Swarm will talk to the other nodes using the Docker API too, which means that you don't need to modify your Docker engines to put them in a Swarm cluster. And so the key idea is you don't change your clients, you don't change your nodes, you put Swarm in the middle, and boom, it acts as a kind of load balancer, but on the level of the Docker API. The Swarm is written in Go, just like the Docker engine, and the original authors of Swarm are also among the original authors of the Docker engine, so that would make sure that those people know how the engine works, kind of. In practice, Swarm has been stable since November 2015, so that's 6 months now. How does it compare with other orchestration systems? That would be a very long answer, but the highlight is that it tends to have a little bit less features. However, it is way easier to set up. And even though sometimes people perceive it because they're like, oh, is there load balancing? Is there stuff like that? And like, no, there is no built-in load balancing directly. You have to put a little extra components, which is what we're going to do today. So sometimes people think that Swarm is the low-key option. Swarm scales well. It scales extremely well. We have been able to run Swarm on a cluster of 1,000 nodes running 50,000 containers without tweaking it. So we take Swarm out of the box. We didn't do any optimization, any change in the code. We just say, okay, we're kind of fed up with people saying that Swarm probably doesn't scale because it seems simple and simplistic. Let's see how it fares. And the answer is that out of the box, it scales to 1,000 nodes without doing any kind of tuning. So that works pretty well. For most of the advanced features, you will need a key value store. And it can use any of the most frequent key value stores. So it can use console, etcd, zookeeper. That's also a kind of differentiator versus other orchestration systems, because most other orchestration systems are tied to one specific key value store. Like Mesos is kind of coupled with zookeeper, Kubernetes with etcd, Nomad with console. So Swarm can use all of them. How do we deploy Swarm? What are the different beasts in the Swarm zoo? We need a cluster discovery mechanism. So we need a way for the Swarm manager to know where are the other nodes located. So that we need some cluster discovery mechanism. We need the Swarm manager itself, which is the thing with which we will communicate and that will communicate with the engines. And sometimes we need the Swarm agent, which is a little thing that runs on every node and will make sure that the node is registered in the service discovery mechanism. So for cluster discovery, there are multiple possible backends. So we can use dynamic discovery. So you run your own console, etcd, or zookeeper cluster, and each node will talk to the cluster and say, hello, I'm node 4, my IP address is 1234, and I'm a Swarm node, I'm a Docker engine, I would like to be part of this cluster. So every node does that, and now in your zookeeper, etcd, or console, you have this list of all the nodes, and the manager just has to connect to that, and you say, oh, those are all the nodes I need to connect to, and that's how it works. If you don't want to set up your own key value store, you can also use something called the token-based discovery, where in fact you will use a key value store operated by Docker Inc. And what happens is that the agent, instead of talking to your key value store, will talk to the key value store hosted by Docker Inc. And that just saves you the hassle of setting up your own key value store. But you can also use static discovery, which means you just give to the manager a list of IP addresses, and you say, okay, those are the nodes you need to manage. At first, this looks like this is not very dynamic and not very helpful, except for basic testing. Unless when you think about, oh, what if I could set the IP addresses of my nodes? What if I could have my IP address plan, and I'm going to decide that all my Docker nodes are going to be 10.0.0.1 all the way to 10.0.0.255. And then you'd give to the Swarm manager a long list of IP addresses, and you say, there you go, this is my cluster. And at first it's like, well, will that work? And yes, that Swarm has been designed to kind of continuously check the cluster members, just in case like you have a cluster member that goes away and comes back later. And it also has been designed to withstand big network partitions. Like you have 1,000 nodes, and suddenly you lose a whole data center and 300 nodes disappear. and then they come back like a few hours later. And Swarm can deal with that just fine. So it's totally fine to give Swarm a list of even like 1,000 IP addresses, and when you light up cluster nodes, you put them on those IP addresses, which is extremely easy to do if you are operating your own infrastructure, or if you are in the cloud and using something like VPC, for instance, which lets you set your own internal IP addresses. Somebody did some benchmarking on that, so there is a link to an article explaining how far you can push this concept. So there is the Swarm agent, which is only used for dynamic discovery. The Swarm agent needs to run on every node, and on a regular interval. By default, it's like every 20 seconds. It will connect to the discovery mechanism and say, hello, I'm a node, and I'm on this IP address, and I would like to be a member of the cluster. If the agent stops, it's OK. Like the manager, once the manager learns about a node, it keeps it forever, and it will keep trying to reconnect, so that's fine. The Swarm manager, well, that's again, we can think about that like a load balancer for the Docker API. It's an extremely rough approximation, but that helps. So it will contact all the cluster nodes, it will do some health checks, it will do the resource scheduling, and keep track of what containers are running on the cluster and on which nodes. So here we are going to use a key value store, and we are going to use it for the cluster membership discovery, but also for other purposes. We are going to use the key value store as a backend for the overlay networks, so the thing that will let us have virtual networks spanning the whole cluster. We are going to use it, not exactly, but for resilient storage of important credentials. That's in the HA section, so we won't see that today. But and if we were to do the HA section, we would also use that for Swarm leader election. And we are going to use console. And the general idea is that we are going to have a console node on each node of the cluster. That way, you can be on any node on the cluster, and you can connect to localhost, and you will find a console node. You don't have to connect to console, but what if that node is down? Oh, wait, I should put a load balancer in front of my console cluster, but that adds even more components. No, instead, you just connect to your local console node. Console is a distributed key value store, so you can connect to any node. It will give you the same view of the data. So, do we really need a key value store? Like, could we do without that? We don't really need a key value store. There are some features that kind of rely on that, but we could also do without. For instance, we could use the token mechanism for cluster membership, and in that case, we don't need a key value store. For the network overlays, we could use a different overlay driver. We could use, for instance, Weave, which is using a CRDT conflict-free replicated data type to distribute the IP address allocation and which container runs where. So Weave doesn't need a key value store. For the storage of credentials, so in the HA section, at some point we would use console to store the important files, certificates, keys, but we could decide to put that in an S3 bucket, for instance, like a private S3 bucket. So why are we using a key value store? Why am I making my life more complicated with this key value store? Because each of those things that I indicated before requires conceptually some kind of key value store. So if I'm not running it, someone else is running it. If I'm using the token discovery mechanism, then Docker Inc. is running this token server thing, and I'm using that. So now I'm reliant, I'm dependent on that. If I'm using Weave, for instance, I don't need a key value store, but Weave is operating some kind of protocol that behaves a little bit like a key value store. And if I'm putting my credentials into a private S3 bucket, now I'm depending on S3 for good operation. So here it's really a choice. And really there is no right or wrong answer. Some people say, okay, I'm going to use external services as much as possible. Let's go serverless, yay, because that's less things for me to operate. Some people will say, heck no, I don't want to depend on stuff operated by people that I don't know, don't trust. S3 is notorious to have spikes in latency and stuff. So for credentials, that's probably okay. But one in another, instead of depending on 3 external services upon which I have no control, I prefer to operate my own key value store, and that way, I mean, at least it's my problem now. So if it's broken, I can fix it. And now I rely on one service instead of 3 different services operated by 3 different people. So here I decided to go with Kronos. I decided to go with Console, but it's a purely arbitrary choice. You can completely go another way if you want. The reason why I was mentioning Kronos is that there is a really good point in against having many different distributed systems like that. In the Mesos ecosystem, Kronos is the distributed cron. So if you have a cluster and you want to run jobs on a regular basis on various nodes, and Kyle Kingsbury did this amazing analysis on Kronos where basically he shows that Kronos can break in many circumstances because Kronos has its own consensus. It relies on Mesos, which has its own consensus, and also relies on Zookeeper, which has its own consensus. So now Kronos can break basically if any of those 3 consensuses are broken. So instead of having a highly available system, you have a highly unavailable system because you have more things that could break. Okay, so should we always use a key value store? No, that's pretty much what I explained. You have always a way to make without it if you don't want to operate it. So why did I pick Console? This is absolutely not like the official way. Console is not like the best key value store or whatever. I personally like it, and I find it relatively easy to set up in that context. So that's why I decided to use it. But if you are more familiar with etcd or Zookeeper, you can very easily use them instead. So we will set up our Swarm cluster. Normally, when you set up a Swarm cluster, so you need to enable communication over the Docker API. So here, we already have the Docker API exposed on port 55555 without certificates and authentication. So we could really easily fire up a Swarm manager and that's it. But I said, okay, opening up port 55555 is not very secure. So we want to set up TLS certificates. And then use that to communicate with the nodes. So we will have a CA, a certificate authority. We will create for each node a key and certificate, for Swarm itself, key and certificate, and for the client, so for ourselves, key and certificate as well. And all those things, all the certificates will be signed by the CA, and the CA will be on each node. That sounds like a lot of work, and yes, it is. Except if you're the kind of people who was born with the OpenSSL man page in their arms. So we're going to use Docker Machine to make that easier and more streamlined. So how to use Docker Machine to set up a Swarm cluster? Docker Machine initially had 2 primary uses. The first thing was when you just need like a Docker host somewhere, and you have some cloud credentials. Maybe you're using EC2 or DigitalOcean, or maybe you have your private OpenStack cloud, and you can use Docker Machine to do Docker Machine create -- driver Amazon EC2 my node, and it will create a VM on EC2, install Docker in that VM, pass some extra configuration, and you have a new node. You can also use it to create nodes on your local machine. If you have VirtualBox or VMware on your workstation, same thing. You use the same kind of command, but -- driver VirtualBox, and now it creates a VM within VirtualBox locally and with Docker pre-installed. And when we started to roll out Swarm, one of the biggest complaints was this is a huge pain in the neck to set up because we have to create those certificates and it's complicated, and that was probably the biggest kind of pain point when you want to deploy Swarm. So we did some integration so that you can, with Machine, you just say, hey, I want this node to be a member of a Swarm cluster, and it will create the certificates and do all the kind of hard work that you had to do normally. The thing is that Docker Machine also comes with a really convenient driver called generic, which instead of trying to create a VM using some cloud API or using some local virtualization software, is just going to connect to an existing machine using SSH and use that machine. So how do we set up Docker machine? On the VMs here, we already have Docker machine. So if I do Docker machine -v, it's telling me Docker machine version 060, okay. And we just, if we were to install Docker machine locally, we would just need to set a few extra environment variables to give our cloud credentials. Here we already have 5 nodes, so we don't need to give cloud credentials. And normally, so when you want to create nodes, they look like that. Docker machine create -d with the driver name and then the node name. Then you can do Docker machine ls and see the nodes that exist. And you can destroy nodes with Docker machine rm, which will destroy the virtual machine using the cloud provider's API. Then, once you have a bunch of nodes managed by Docker machine, there is a Docker machine env command that shows you the environment variables that you should use to talk to them. Before, we would just manually do Docker host equal TCP, blah, blah, blah. Now we will have Docker machine do that for us. And if you need to do some low-level debugging, there is Docker machine SSH to automatically get an SSH connection in the machine. So a few words about that generic driver. All other drivers work the same way. When you do Docker machine create, it's like create the VM using the API of the cloud provider or the API of your local virtualization software. Then connect over SSH, detect what kind of stuff we have. Is it Ubuntu? Is it Fedora? Where is the config file for Docker? How do I install Docker? And then do the configuration. When you use the generic driver, we just skip the first step. We don't create the VM. It already exists. We are just given the IP address and the user to connect. And so the generic driver establishes an SSH connection to the machine. It's like, what do we have here? Oh, it's an Ubuntu 15.10 using systemd. So the configuration file is in /lib/systemd/whatever I showed just earlier. Okay, that's just what I did. So this is how we are going to provision the first node. So this is a pretty big command line, so that's where I definitely recommend that you have the slides and copy-paste that from the slide, except if you type extremely fast. I forgot to mention it in the beginning, but in the bottom right corner, you can see the slide number. So, sorry? All right, let me try something. That's okay. So I hid it extremely carefully, but that was the slides that I had on screen weren't the right ones exactly. I had made some changes, and I think my browser was still showing what I had in cache. And so I was thinking, oh shoot, I forgot to deploy the right version of the slides, but no, it was just my browser cache. All right, lesson learned. So how do we provision the first node? Yeah, so bottom right corner says slide 90, and if you put #90 in the URL bar, it will go directly to slide 90. So I'm going to paste that to my node, and then I will break down that command for you to explain what all those parameters stand for. Perfect. So Docker machine create -- driver generic. So use the generic driver. Don't create a VM. Reuse a VM that we already have. -- engine opt. So -- engine opt means pass the following option to the Docker engine. And in that case, the options are cluster store and cluster advertise. Cluster store means we want the Docker engine to use that cluster store for overlay networks. So overlay networks are this feature that lets you have a network spanning multiple hosts. And when you have that, you need, among other things, to know which IP addresses are in use, because if you have 2 hosts starting a container at the same time and picking the same IP address for a container, that's gonna end badly. And we need to keep track of which container is running where, so that when my container is trying to communicate with another container, so it has resolved the IP address of the container. That IP address is 1234. Now it's sending a packet to 1234. So that packet is kind of going out of the container, and it's reaching the engine, and the engine is like 1, 2, 3, 4. Is that local or remote? If it's local, you just bridge it directly to the other container. If it's remote, where should it go? Like, I can't send that packet on all over the network. I could if I were running on my own infrastructure and I had an actual Ethernet network and I could use broadcast or multicast. But I'm in the cloud and I don't have broadcast and multicast because in the cloud nobody can hear you scream. So I end up having this table in my key value store telling me IP address 1234 belongs to this container which is on this other host. And so when my Docker engine sees a packet for 1234, it knows exactly to which node it should be sent. And so that's why I need a key value store. And so that's why when I set up my Docker engine, I pass those two flags, cluster store to say which key value store to use, and cluster advertise, which means which IP address should I indicate that I have to the other members of the cluster. So you're going to tell me, wait a minute, cluster advertise is ETH02376. That's not an IP address, right? The Docker engine will it will recognize that ETH0 is an interface, and it will read the IP address that this interface has. So instead of having to put the IP address here, I can put the interface, and the engine will automatically expand that to the IP address, which makes my life way easier. Then I have Swarm-specific flags, --swarm, --swarm master, --swarm discovery. --swarm means I want this node to be member of a Swarm cluster. So in addition to deploy the engine and set up the engine, I also want to run the Swarm agent so that this machine will register itself with the discovery mechanism. And that's why I have --swarm discovery. And there again, I have console, and so I'm telling to the Swarm agent, this is the address where you should register yourself. And then --swarm master means, in addition to all that, I also want to run the Swarm manager on this node so that I can connect to it and address my whole cluster. And then I have the options specific to the generic driver, generic SSH user, so which user should we use to connect to the node, so that's going to be Docker. And -- generic IP address. So here I'm going to put the IP address of my node. Once again, please put the IP address of your node, not mine. Otherwise, there are going to be two instances of Docker machine trying to set up the cluster, and that will be bad. And then I put the name I want for my node, node1, and I send this. So it's the first time you use Docker machine, it will create the CA. Then it will create the client key and certificate that we are going to use to connect to everything. Then it's creating the machine, which in that case means skipping that because the machine already exists. Then it's connecting with SSH to the machine. It's like, what do we have here? Oh, we have an Ubuntu machine with systemd, so the config file will be in that location. Let's install Docker. Oh, Docker is already installed. Great, let's keep that and directly drop the configuration in the right place. And then it's setting up Swarm, which means starting Swarm agent and the Swarm master, and that's it. If I do Docker PS, I can see the two containers I was talking about, like Swarm join, so this is the agent, and Swarm manage, that's the Swarm manager. If I do Docker machine ls, now it tells me I have a node called node1, provision with a generic driver. That's the address of the node, and it's running engine 111.1. I'm going to give a few seconds for people who are trying to deploy that. Yes?
So the generic IP address is used for what? Why can't that be?
So the generic IP address is used for what? It's used, or it's just used by the generic driver to know what it should connect to. Could I use node1 here? That's a good question, and somebody asked me last time, and I forgot to double check. I think you should be able to use node1, yes. And I think machine will be smart enough to do a DNS resolution and be like, okay, it will be pretty much the same result. I'm not 100% sure because it might then put the value here somewhere else. And in that specific case, node1 works, like I can ping node1, but it's not in the DNS. So if I'm on some other points of my cluster, like if I'm in a container, and in my container I do ping node 1, that will not work. Because in the container, there is no entry in /etc/hosts mapping node 1 to the IP address of node 1. So that's why, to be on the safe side, I put the IP address here. But putting an FQDN, a full domain name, would work just fine, yeah. Okay. So now we want to provision the other nodes, and the command that we are going to use is almost the same, with one difference. We just remove the swarm master flag because we want to have only one manager on the first node. And to make things easier, so to avoid like having to type the IP addresses of all nodes, I'm using a little bit of shell scripting. I'm grepping the entries in /etc/hosts, and I'm mapping them to IP-ADDR and node name, and using that in a little shell for loop. So I'm going to blast that to my terminal here. And so it's connecting to, it's creating a key and certificate for node 2, connecting to node 2, be like, oh, this is an Ubuntu machine with systemd. Okay, let's install Docker. Oh, Docker is already installed, so let's move to the next step, which is deploy the certificate and set up Swarm, and then we're done, and we move to node 3, and then node 4, and then 5. And that's it. So now we have our 5 nodes. If I do Docker machine ls, I see node 1, 2, 3, 4, 5. Great. So how do we use those? So I mentioned earlier Docker machine env. Docker machine env, you give it the name of one of your nodes, and it will output the variables that you should use. So if I do Docker machine env node 1, it tells you, you should set Docker host to this, but you should also set Docker TLS verify and Docker cert path. Those 2 extra variables are the one that will tell to the Docker client to use TLS when connecting to the Docker machine. Like, just to show you, like if I just set Docker host and I do Docker PS, it will telling me, malform HTTP response. Are you trying to connect to a TLS-enabled daemon without TLS? It kind of guessed what was wrong, because many people had that problem. So instead of having a weird error message, we're trying to guess what's going on. So if I want to enable TLS, the easiest way will be to do eval $parenthesis on this Docker machine env node 1 command. This just means execute that and feed that into the shell. So I'm automatically setting all the correct underlying variables. And you can see that in the prompt here, there is a little fancy thing that shows us which node we are currently talking to. Before it was local, like there is no Docker host variable, so we are talking to the local node. And now it shows correctly node 1. And later, when we will be talking to the Swarm cluster, it will show Swarm. Yay. So if I do, let's say, Docker version, it tells me client 111.1, server is 111.1, Docker PS, I see my 2 Swarm containers, Docker info, that's a bunch of info about my cluster node. And by the way, I can see the Docker engine flags here, cluster store and cluster advertise. And you can see that cluster advertise, which was ETH0 to 376, has been correctly expanded to the internal IP address of my EC2 instance, colon 2376. All right, so when I'm doing that, I'm talking to node 1, and it's exactly as if I was talking over the normal socket. The only difference is that I'm connecting over TCP and using the TLS certificates to talk to it. Is it the time of the coffee break? No, not yet. So that's great, but now I want to, oh yeah, I wanted to show that I can interact with that node completely normally. Like I can do Docker run, --rm, busybox, echo hello world, and that works. So even though this node is a member of a Swarm cluster, I can still interact with it directly just fine. So this means that if down the road at some point I have problems with my cluster and I want to troubleshoot a single node, I can use the Docker API just fine. Okay, so now I want to do the same thing, but I want to talk to my Swarm cluster instead. And for that, let's look at what happens when I do Docker machine env node1 -- swarm. I get almost the same output with and without -- swarm. And if you're wondering what's the difference, because really it looks so close. So if you're like a pro in find the 7 differences, then yeah, the port number, someone saw this. That's the only difference. Without the -- swarm flag, we're talking to 2376, which is the default port for the Docker engine over TLS. With -- swarm, we're talking to 3376, which is the port where the Swarm manager container is listening. All right, so let's enable Swarm. So eval that whole command with -- swarm. In the prompt, I'm sorry, like the green thing on the screen is not super readable, but here we have Swarm instead of node1. And now I'm going to do Docker version. And yeah, in the server side, it's telling me that I'm talking to Swarm version 1.2.3, which was released 2 days ago. I forgot to update the slides to indicate that exact version number. But, all right, so can I start a container now? Like, oh, I can do Docker info. Here, things start get weird. Like, if I do Docker info, I have an output which is different from earlier. I see nodes 0. And if I do Docker run --rm busybox echo hello world, it's telling me error response, no healthy node available in the cluster. So does anyone have an idea why there is 0 node in the cluster and why the cluster doesn't work? Yep, console. We're missing console. So the interesting bit is that even though I told my cluster that we would be using console, I didn't deploy console, and yet things still work. So this is Docker being nice and lazy. Lazy because it doesn't try to connect to console until we really need it. So if I want to run a local container, like if I directly talk to a node and say Docker run busybox, like yeah, I can do that just fine. I don't need console for that. I only need console when joining a Swarm cluster, and I only need console to do overlay networks. But if you don't ask me to do any of those things, that's just fine. So I have a Swarm manager which is trying to talk to console, but console is not there yet. So the Swarm manager, instead of getting a list of nodes, it gets an empty list, and on the side it logs an error saying I could not connect to console, something's probably wrong. And at the same time, the Swarm agents are trying to register themselves into console, but same thing, console is not there yet, so it doesn't work. So we need to start console so that our cluster works correctly. So we're going to run console in containers because we can. And so that gives us a really interesting picture where Docker relies on console, but console will be running inside of Docker. And we can do that because of this kind of laziness of Docker, where it doesn't insist on connecting console. Instead of like, oh, console is not reachable, so I'm aborting and quitting and crashing and burning. Instead, it's like, well, some features will not quite work, but that's okay, let's try anyway. And as soon as console becomes available, then all those features become available as well. We are going to use the official console image. We are going to give a few extra flags to Docker about those console containers. We are going to tell Docker, I want you to restart those containers automatically, because console is going to be an essential piece, cornerstone of the system. If console is down, a lot of things are going to be down as well. So we're going to tell Docker, if this container crashes or stops, restart it right away. Likewise, if we restart the Docker engine, automatically start the console container. Another thing is that we are going to use host networking. Host networking is when you have a container that is using the network stack of the host. It means that this container has access to the interfaces and IP address of the host. Why are we doing that? Because if we start console in a normal container, then we have to tell to console, okay, so you think your IP address is 172.1702, for instance, on the internal bridge, but in fact, the IP address as seen by the other nodes is 172.168.2.33 or whatever the internal IP address of the EC2 VM is. So we need to tell console about what IP address it is reachable on by the other nodes. We need to map a bunch of ports that will be used by console for its HTTP API, for intra-cluster communication, for WAN communication, etc., etc. So instead of that, we're just using host networking. So from a network standpoint, it's as if console was running directly on the host, but for software management, packaging, and isolation standpoint, it's still running in a container, so it's cleanly isolated. Host networking, yeah, that's exactly what I just explained, great. And this is why we are using Docker Machine 0.6. In Docker Machine 0.6, the Swarm containers, so the Swarm agent and the Swarm manager are started in host networking as well. The Swarm manager and the Swarm agent need to talk to console. And so if you remember, when we started all those things, like in those flags over there, we did put like a Swarm discovery console : localhost : 8500. So it means that the Swarm manager and the Swarm agent are going to talk to localhost to connect to console. So when the Swarm containers are in the host network stack, and console is in the host network stack as well, they can connect over localhost just fine. But with Docker Machine 0.7, the Swarm containers are in their own network environment, and that doesn't work anymore. So until we have a flag for Docker Machine to pick which network model we want, I'm sticking to Docker Machine 0.6. A few words about console. Because if you never deployed console and if you never ever deployed even like a key value store, like a distributed key value store, it's useful to have a little bit of information. Almost all those key value stores, like etcd and console, use something called Raft, the Raft protocol. Zookeeper is using ZDB, which is a kind of variant of Paxos. So it's a consensus algorithm that the nodes run among them to kind of vote on what's happening in the cluster. To give you a really super quick overview of how those distributed systems work, it's as if together we had to decide on when we're going to do the coffee break. And strong consensus means that we want to have a quorum. We want to make sure that at least half of us agree on what should be the time of the coffee break. And then when we want to know what is the time of the coffee break, we need to make sure that the group to whom we ask is also made of at least half of the people. This means that, for instance, let's say if the small group in that side of the room wants to change the time of the coffee break, but we have a network partition, so we can't communicate between like that side and that side, then the people here don't have quorum. They don't have the majority, so they say, okay, there is not enough of us to change that, so we can't change the time. However, that group has quorum. They have the majority, so they can change the time. And it means now if we have a different network partition later, like if the network partition is now this, the people here don't have majority. So when they want to be sure about the exact time, they're like, there's not enough of us, so we're not sure that we have the right information. But the people in that group have, there's a guarantee that there is at least one person in the majority group which was present in the group who voted about changing the time of the coffee break, basically. That's how strong consensus systems work. All right, so the protocols ensuring that have a very particular behavior. The more nodes you have, the slower they get, which at first seems weird, but intuitively, if you have to agree about time of the coffee break or where should we eat tonight with 3 persons, it's pretty quick. If it's 300 persons, it's way longer because you have a lot more communication happening. And so that's why when you have such a system, whether it's ZAB for Zookeeper or Raft for console and etcd, it's recommended that you have 3, 5, 7, maybe 9 nodes, but really not more than that, because then it's become overkill and performance goes really, really bad. And it's always odd numbers so that you can have a strong majority. So in that case, we have 5 nodes. So we can say every single node is part of the consensus thing. Now, if we had many nodes, like let's say more than 10, we would pick a small subset of 5, 7 nodes, let's say, and decide, okay, those are going to be server nodes in the consensus terminology, and all the other nodes are going to be simple agent nodes. The simple agent nodes don't take part in the Raft protocol. They don't vote about like writes and reads and stuff. When you talk to an agent node about, hey, I want to get the value for this key, they will transparently proxy the request to one of the server nodes. And it's completely transparent for you. So when you are on a node that has a console running locally, you just talk to console, make your request. You don't have to worry if it's a server or an agent. It will work the same way. All right. So I think now is the time of the coffee break, but I will, just before we go for coffee, we will start this so that if people want to catch up, they can also use the break to catch up, and we just have to paste that command to our terminal, and I will explain what this command does. So first, we are getting the IP address of the current node. That's the first line, like IP address equal IPALS. This is just reading the IP address from ETH0. Then we are going to SSH into each of the 5 nodes one by one, node 1, 2, 3, 4, 5, and on each node we are going to do docker run, so start a container, -d, start it in the background, -- restart equal always. If anything bad happens to this container, i.e. if it stops, crashes, or whatever, restart the container right away. -- name, so let's name the container console_node 1, 2, 3, 4, 5. Then -e, that's to pass an environment variable that will be used by the console startup scripts, console bind interface equal ETH0. That's the equivalent of the cluster advertise option. It tells to console, you should bind to this specific interface and announce this interface to the other nodes. --net host, to use the host network model. Console is the image we want to use. Agent means run an agent. -server means and that agent shall also be a server. -retry join means we want to join a cluster and we want to retry, so we basically want to retry forever until we manage to reach the cluster, and we want to join on the IP address, so the IP address is going to be the IP address of node 1. And last but not least, well, 2 more things, bootstrap expect 5. So this is because if we go back to my vote for coffee break analogy, if it's just that portion of the room trying to vote for coffee break, if they never heard about the other people, they have no idea if they have the majority or not. It's like, okay, it's like 6 of us, but do we have majority or not? Did we have 10% in the room, and in that case we have majority? Or did we have 50% in the room, and in that case we don't have majority? So bootstrap expect 5 tells us we're going to have 5 nodes. So as soon as we have 3 nodes together, they're like, we have majority, we can start. And the last 2 flags, -UI and -client 0000. -UI means that we want to expose the web UI. It's not enabled by default, but it will give us a nice debugging tool. And -client 0000, this means we want the API to be exposed to 0000, which means anybody will be able to connect to the API. Those last two flags are not necessary. They are just here so that we can talk to the API and we can use the UI. But in production, you typically don't want them. And so when I do that, say, OK, connecting to node 1 to start the console container. Then it's connecting to node 2. Then node 3, and each time you have to type yes, because it's the first time you SSH to that given node, and you have to validate the SSH public key. Node 4, and finally node 5. And at this point, our console cluster should be up, which we can check with docker run, --rm, --net host, console members. That's just a console command to ask console, hey, what do you, whoops, right, I have to switch back to my default node, so eval docker machine and node 1. And then it's telling me, yep, I have 5 nodes in my cluster. And if I do docker info, so I go back to the Swarm cluster, and I do docker info. Sometimes it can take a few minutes, but eventually we will have our 5 nodes. Here I have 4 nodes. I know because it says CPU 8, and I know I have 2 CPUs per node. So at this point, I only have 4 nodes in the cluster. But yeah, if I give it 1 minute more, I have all my 5 nodes. All right, let's go for coffee. This is a good sync point if you want to catch up, if you want to have your cluster up and running. I will be here if you have questions too. And let's regroup in 20 minutes. So I'm going to kind of resume by showing a couple of console tips and tricks. So we saw the console members command that tells us basically the view of the cluster according to console. But we can also use the web UI. So I can go to any of my nodes, I can put any of my IP addresses on port 8500, and it should redirect me to /UI, and I should see a nice web interface if the network cooperates, which is not a given. No, this seems to be connected, so that should work, in fact. Let me try on another node. Right, if I keep typoing the IP address, that's not going to work. I got redirected to /UI, so that should, yeah. So I have something like that. I can go to nodes and see that my 5 nodes are up and running. There is a little green thing here, which means good. And I can query the key value store. So in the key value store section, I have Docker, and in Docker, I have, for instance, Swarm. And in Swarm, I have nodes, which lists the nodes that I have in my cluster, for instance. So that gives you some extra debugging tools. All right, I'm going to close a few of those extra tabs. 2. All right. So at this point, yeah, I wanted to go back to the Swarm cluster, and if I do docker info, in the output of docker info, instead of having information about a single node, I have overall information about my whole cluster, and I have a view node by node. I have this is node 1, and then node 2, and then node 4, 3, 4, and 5. So that gives me a kind of overview of my cluster. I can run stuff on this cluster. So I can do, for instance, docker run -d -p Redis. So it means start a Redis container and make it available on the network. And now if I do docker ps-l, Remember, like in the port section, before I would have 0000 colon port 32768, for instance. Now I have the exact IP address of the node on which Redis is running. So it looks as if my Swarm cluster was one big Docker machine with multiple network interfaces, each with its own IP address. And so when I start a container and that container is published on the network, boom, it's bound to one of those IP addresses corresponding to the node on which it's actually running. All right. The Swarm will schedule the containers on the cluster, and it can do that following different strategies. So there is the random scheduler, which means just put containers at random. There is spread, which means try to spread the load across the cluster, which really means place the container on the node that has the lowest count of containers, including stopped containers, which can be a little bit weird because, like, if you, let's say you have 100 stopped containers on one machine, and on all the other machines you have 10 containers. When you start a container, you would think it's going to go on the node that is not running containers. No, it's going to go on the node that has the lowest count of containers, even if those containers are running or stopped, it doesn't matter. Then there is the bin pack strategy, where instead, Docker will try to fill up the nodes as much as possible. So instead of picking the node that has the lowest count of containers, it will pick the container that has the highest resource usage, still respecting the resource allocation for the containers. So let's see what about like resource allocation. How does that work? When you start containers, you can indicate how much resource you want to reserve. Let's do a little example with memory. I'm going to start a Redis container, so docker run -d -m 1G, so I want 1 GB of RAM and Redis. So I do that, and it starts me a Redis container instantly. Great. Let's start another one, another Redis container. Great. And 3, 4, 5, 6, 7, 8, 9, 10. So my instances have 3 point something gigs of RAM, and I have 5 instances, so I should be able to start 15 Redis containers. So 5 more. 1, 2, 3, 4, 5. And then the last one, I will get no resources available to schedule container. And now if I do docker info, in the output of docker info, for each node you can see reserve memory 3 gigs over 3.8 something. Okay, so that shows us how we can start containers very easily and give them a resource quota and have Swarm automatically place things wherever we want them to be. So now we have to remove all those containers. So let's do a little bit of shell scriptery. So docker ps, pipe, grep, no, let's do awk, /redis, and print $1. So that means get me all the containers, all the lines that contain Redis, and print the first column, which is the container ID, xargs docker rm-f. And now, so we have a Swarm cluster. We have console, so we have a backend for overlay networks. So we're going to see how to use overlay networks. So networks, how do they work? Since Docker 1.9, there is the concept of networks. A network is kind of a virtual switch to which you can connect containers. By default, all the containers are on the bridge network, but there are other network models. For those who were there this morning, I demoed like the bridge driver, but also the non-driver, the host driver, the container driver. And so you can create additional networks. You can like create a private, isolated network for a specific application and put containers on this network. Containers can also dynamically join and leave networks. So you can like create a container which is on one network and then connect it to another network, disconnect it from the first one. You can put a container on multiple networks at the same time. That works just fine. And you have network aliases, so you can start containers and give them a name, so that when they are on this network, the name on this network and only on this network will resolve to the IP address of the container. And you can give the same network alias to multiple containers to have DNS round-robin load balancing. So how does that work? Typically, we will use Compose to automatically create and manage networks because it's just easier. And that leads to something I call YAML-defined networking. So it's even better than software-defined networking because it's easier. You have a nice YAML file describing networks and containers. If you want to manipulate networks manually, you can do that with the Docker CLI. There is Docker network that has like Docker network create, Docker network ls, Docker network rm. And when you do Docker run, you do Docker run --net some network, --net alias some network alias. You can put --net multiple times if the container is supposed to be on multiple networks. And so I have a little example. We're going to do that. So first, let's make sure that we are talking to our Swarm cluster. Yep, check. So now we're going to do Docker network create blue and green. And we are going to create containers for blue and green things. So Docker run -d --net blue --net alias things --name the sky is blue. So let's have a container for the sky, and that's going to be Redis. Then let's have another blue container. So that's going to be the sea, and now let's have a few green containers. So --net green --net alias things --name the grass is green, and let's have also the forest. Now if I do Docker run -ti --net blue alpine sh, so I'm creating an alpine container in the blue network. And so when I'm in the blue network, I can do ping sky or ping sea. I can ping those containers just fine. However, I can't ping the containers in the green network. That doesn't work. If I want to reach those, I have to put myself in the green network. And now if I do ping green, ping grass, that works. So you might think, okay, so I can't resolve the names, but maybe if I put the IP address directly, I will be able to ping the blue network from the green container. So if I put like this address here, no, networks are isolated. I also have the things network alias, so I can do ping things, and it's going to give me the IP address of one of the containers that has this network alias. And I can use like NSLOOKUP. I can do NSLOOKUP things, and it's going to give me the IP addresses of all the containers that have the things network alias. So in the green network, things will map to grass and forest. In the blue network, things will map to sea and sky. Okay, that's pretty simple. So I'm going to remove all those containers now. Docker rm-f, sea, sky, forest, grass, and Docker network rm forest, green and blue. Okay. Yep. A few things like about operations if you're using overlay networks. After a crash, if you try to remove a network, sometimes it could tell you, I can't remove this network because there are still active endpoints on it. Because Docker thinks that there are still containers connected to the network, and it refuses to remove the network. So you can't do Docker network rm-f. However, there is a Docker network disconnect-f that you can use to force those endpoints to be removed, and then you can use Docker network rm-f. That's a little usability thing that we're going to improve in the long run, so that if you really want to, you can just remove a container immediately. Okay, so checkpoint. We have a Swarm cluster using console for membership discovery and also for overlay networks. We have a way to create networks spanning the cluster, and we can create containers that communicate with each other. So now we want to, okay, how do we run this Docker Coins application on the Swarm cluster? Well, the first thing is to build it. So what happens if we try to build on Swarm? Like I'm on my Swarm cluster, and I do Docker build or something like that. What would happen? So this would work, but there will be some little gotchas. What will happen when I do a Docker build is that one node will be picked at random by Swarm, and the build will happen on that node. But if I do another build later, maybe it will pick a different node, which means that caching might not work, because on this node I have all my layers and my cache, but on this other node I don't, and so when I build, it will rebuild everything from scratch. That's a first little problem. Another problem is that when I do a Docker build, my image will be present only on that specific node, not on the other nodes of the cluster. So if I try to run the container on another node, it will not work because the image is not there. So this means that not only you can have like scaling problems because you built on one node and you can't start on the other nodes, but worse, you can have consistency issues because you build on a node, so you have v1 on a node. You do some changes and now you build, and the build ends up on another node. So now let's say that your container image is my app. So you have my app v1 on that node, my app v2 on that node, and now if you try to scale my app, Swarm will be like, okay, fine, I'm going to start containers on both nodes, but you have different versions of your application. That's no good. So think about this scenario. I do Docker Compose up, so that I will build every single service on a different node, and that at first, it seems like it works. Then I do Docker Compose scale. Here, I have a first problem, but it's well hidden. It's just that when I do scale, all my scaled containers are on the same machine because only that machine has the image for this service. But if I don't pay too much attention, I won't see it. Now I do Docker Compose again after making some changes. So I'm building, but possibly on different nodes. And now, when I scale, I can have containers on the first node and the second node, so I have a mix of new and old containers. The perfect solution, like in an ideal world, would be that when you build, there would be like a hidden distribution mechanism between Swarm nodes, maybe using some peer-to-peer stuff, like something close to BitTorrent, because that's super efficient to distribute things across a cluster. And some people might or might not be working on that. But meanwhile, we have to distribute images ourselves. And also, when we reference images, we should reference them with an exact version tag. Because if we just do my app, as opposed to my app colon this exact version hash, then we will end up with potentially different versions running on the cluster. So couldn't Swarm do that automatically for us? So I mentioned like this idea of having some peer-to-peer distribution mechanism, but that requires some pretty deep changes in the Docker engine, because instead of talking to a registry, it should talk to a distributed registry. So can we do that with what we have today? Like, couldn't we have Compose and Swarm do that automatically? Yes and no. We could decide when I do Docker build, I'm going to build on all the nodes of my cluster. At first, it seems like a good idea until you have a 1,000 node cluster, and when you do Docker build, you build in parallel on 1,000 nodes, and that's a really bad idea, because when you will install packages, you will essentially do a denial of service attack against the mirrors having packages that you use in your build. So another idea would be maybe we could like build on a subset of nodes and then run the application on those nodes, but how do we know on which nodes we are going to run the application? That doesn't work. So there could be some ideas about, well, we could have some defaults into Compose and Swarm agreeing on where we should build, where we should run. The problem with sane defaults is that it really depends on your idea of what sane means in that case. Like, we could decide, okay, we're going to build on a node, and then we're going to automatically push the images to the Docker Hub. That's great, except if you don't want your images to be on the Docker Hub. Or we could say, okay, we're going to push the images automatically somewhere. Yeah, okay, that's still great, but it means now you need to have a registry running somewhere, even if you don't want to. Maybe you're using Swarm, but you will only be using pre-made images, and so you don't want to care about builds. So what we're going to do is that we're going to easily assemble our own deployment pipeline using a few really simple Python scripts. So what we will do is that we will build on node 1. We will pick a node and say, that's going to be the node for builds. That way, all the builds happen here, so caching works, and then we're going to get the images from that node and push them to a registry, and that way the other nodes can get those images from the registry. And after doing the build, we are going to generate a new compose file, and in this compose file, all the build services will be replaced with image service. So if I have like build hasher, instead I will have use image from this registry where we just happen to have pushed the thing a few seconds ago. So which registry do we want to use? Here we have a choose your own adventure thing where we could use the Docker Hub. So advantage, it's like zero setup, cost nothing for public images. Downsides, it's hosted in US East and it's hosted by Docker Int, which you might or might not want to trust. Then there is Docker Trusted Registry, which is like a commercial product that we have when you want to run the registry on your own stuff. But there is also the open source registry that you can run yourself very easily. So if we wanted to use the Docker Hub, we would just have to set we would have to create a Docker Hub account and set an environment variable to indicate our Docker Hub username. If we wanted to use Trusted Registry, we would have to go to a bunch of hoops because, well, it's a commercial product. There is like a free trial and stuff, but I don't want to do that. I want to show you only open source stuff. And so we're going to use the open source registry. Running the open source registry is super easy. You just need to run the registry :2 container. It's :2 because registry will be the V1 container, the V1 version of the protocol. And we want to use V2 because it's way better. The open source registry, by default, stores layers and container images in the local file system. If you want, you can very easily configure it to store into S3 or Swift or any kind of object store. And that's a really good idea because it scales extremely well. There is a pattern where, let's say, you configure the registry to store into an S3 bucket, and then you spawn one instance of the registry on each node of the cluster. Because the registry, in that case, stores nothing. It differs everything to S3. So if you store to S3, you can just put like one copy of the registry on each machine, and you get like an infinitely scalable registry, kind of. A thing to know is that Docker requires TLS when communicating with the registry. So if you deploy your own registry, you have to either get a TLS certificate, for instance, from Let's Encrypt, or add an extra engine flag in secure registry and put the IP address of the registry to say, yes, it's OK to connect to that registry without TLS, or host the registry on localhost. So at first, it's like, well, if I host my registry on localhost, it's going to be on only one machine, and I won't be able to use it from the other machines, unless we do this. So this, on the left, we have a container. So this is not super readable, but on the far left, this is backend, and below it, there is like storage for the images. So this is the actual registry container. And then I have something called frontend, and that frontend runs on every single node of my cluster. It's listening to localhost port 5000, and it's sending traffic to the registry, which means that I could be anywhere in my cluster. I can connect to localhost port 5000, and that will redirect me to the backend. So that way, the Docker engine is happy because it's connecting to localhost, so it doesn't require TLS, and my connection is still securely transferred to the backend. And this registry is only reachable from the cluster itself because each front end is bound to localhost. So if I'm not on the cluster, I can't communicate with the registry. And to deploy that, we have a little compose file. So let's go to orchestration workshop, registry. And here I have a Docker compose YAML. So let's have a look. I have backend, which is just like image registry :2. And then I have front end. And how does front end work? It's going to use, once again, the jpetazzo/hemba image, and it will act as a one backend load balancer. So it listens on port 5000, and it sends traffic to backend :5000, and it has a port mapping, so localhost :5000 :5000. So it means bind only port localhost 5000 and map it to port 5000 inside the container. All right, let's just bring that up. Docker compose up-d. So the compose file has depends on backend, but where is the definition of backend? It's just above. The depends on here is just like a dependency information for compose so that it starts backend first and front end after. Why? Because when the front end starts, jpetazzo/hemba, it's just a shell script that generates an HAProxy config file and then starts HAProxy. In the HAProxy config file, it will put like a front end listening on port 5000 and a definition for the backend, and the address, like the host name, will be backend. So it will try to resolve backend to an IP address. If we do that, when the backend container is not up and running, then the name resolution will not work, and HAProxy, when it will start, will be like, wait a minute, backend is not the valid host name, so I can't start. So we put depends on so that the HAProxy will start only after the backend container is up and the backend name resolves to an IP address. That's why there is depends on. Okay, so at this point, if I do docker compose ps, I see that I have backend, so the actual registry, and one front end. But I want to have one front end on each node of my cluster. Let's do that. So I'm going to do a little for loop for n in sec15, do docker compose scale front end equal $n, done. And I'm scaling one by one instead of directly scaling to 5 because there is a little race condition in the scheduler that happens sometime because I'm binding a port, and so sometimes the scheduler will try to put the new container, like two new containers on the same machine, and then it will fail because they both bind the same port. So I have to scale up by increments of 1. That's a minor bug that will be fixed in Swarm soon. So now, if I do docker compose ps, I have my front end and my 5 backends. All right, so now I can go to any point in my cluster, and I can do like curl localhost 5000 slash v2 slash underscore catalog, I think, something like that. And at this point, my local registry is empty. There is no image, there is nothing in it. So we're going to put something in it just for testing purposes. So we're going to pull busybox. Then I'm going to retag busybox. So that's now it's localhost 5000 slash busybox. And I'm going to push that. That's it. That was really fast because the busybox image is so small. And now if I curl again my registry and I ask for the catalog, it will tell me now you have repositories busybox. Yes?
When you Docker compose
what kept the front ends from coming up two front ends on the same machine is that Docker is aware that, okay, front end is binding to port 5000. I mean, it's mapped to port 5000. And so it considers port 5000 as a resource. So when it sees like, let's say I'm scaling from 3 to 4. So I have my 5 nodes, and I already have front ends running on those 3 nodes. And now I'm trying to scale to 4. So it's like, well, you want port 5000, and port 5000 is already in use on those nodes, so I can only put you on the 2 remaining nodes. And then it pick one of those, let's say that one. And when I scale to 5, there is only that last one which is available. And if I try to scale directly to 5, I could be like, it will be, oh, you want 2 new containers? Oh, those 2 nodes are available. Oh, I'm going to put the 2 containers on the same node, and then you get a conflict. All right, so we have a local registry. It works. So now we have to build our Docker Coins application and push the images to the registry. We're going to slightly change our compose file before doing that. So what we're going to do is that we are going to remove some of the port section in the compose file. So I'm going first to go back to orchestration workshop Docker Coins, and I'm going to edit the Docker compose YAML file. And here I'm going to remove that port section, because I don't need to map RNG to a public port anymore. And if I map it to an explicit port number, then I will be only able to scale to 5, because I only have 5 ports 8001 on my cluster because I have 5 nodes. Same thing for Hasher. Then for WebUI, I'm not going to scale the WebUI to crazy numbers, so I can keep the ports, but I will remove the volumes. For Redis, I'm going to go back to a normal Redis container. And everything else can remain as it is. So that's my new compose file. So now I need to build every single container, tag it, push it to the registry, and in the compose file, change the build with image and the image that I just pushed to the registry. And to automate that, there is this build tag push script. And I thought I had a clickable link here to show you what it looks like. So let's navigate here instead. Bin build tag push. So what it's doing is that, well, first it will complain if you haven't set the Docker registry variable. Then it's going to compute the project name. With Compose, the project name is the name of the current directory. So that's why you might have noticed when you do Docker Compose up for Docker Coins, it creates containers named Docker Coins _ blah, blah, blah. And for the registry, it created containers named registry _ blah, blah, blah. The way it knows what to use, it just looks at the name of the current directory. So if your application is in the directory foo, then the containers will be named foo _ blah, blah, blah. So we just do exactly that. We get the name of the current directory. We generate a version number. Here, I'm just using the Unix timestamp, but you're welcome to use like a git hash. That's also a good idea. Then we execute docker compose -f docker compose YAML build. So we build all the Docker Compose build. It's part of the Docker Compose up workflow, but it just builds the images, but without starting the containers. Then we load the compose file, and we parse that compose file. We identify every single service that has a build section, and we generate the name of the image that has been built, and this is pretty easy. If you are in the Docker Coins application and the container name is Hasher, then the image will be Docker Coins _ Hasher. You can see that if I do like Docker images, you can see here like all the Docker Coins _ something that show up. Okay. Then So we tag that so that Docker coins hasher becomes the address of the registry / Docker coins hasher colon the version, which is the Unix timestamp. And you will see that once I execute the script, it will be, I think, a little bit more clear. And then we patch the compose file, so we remove the build instruction and we put the image instruction instead, and we spawn a Docker push in the background for that image. And at the end, we just save to disk the patched compose file. Going to see that in action. So the first thing, I'm going to switch back to talk to node 1, because remember, I want to do all my builds on node 1. Then I set my Docker registry variable to localhost colon 5000. And then I invoke /bin/build tag push. So it's building the application. Since we already had built the application before, so this is super fast, then it's pushing to the registry, and that's going to take a few minutes, especially for the first push, because it has to get all those base images and all the layers into the registry. Questions while this is pushing? Nope. Should have had more coffee. So at the end of the push, it tells me writing a new compose file, and it says compose file equal docker compose YAML dash blah, blah, blah. And so the number here is the version number that was generated, and it writes it like that because in the subsequent commands, I want to tell compose to use that compose file. And one easy way to do that is to set the compose file environment variable. So I can just do export and copy paste that line, and I'm set. So let's see what is in this compose file. So as I said, every build line has been replaced by an image line. So first, if we look at Redis, for instance, it was already image Redis, so nothing has changed. But the 4 other services are now using image localhost colon 5000 / the name of the image colon the exact version that we built. And if I do if I query my registry, I check the catalog. Now it tells me you have BusyBox, but also Docker coins hasher, Docker coins RNG, WebUI, and worker. All right, so the last step is to point my API to the Swarm cluster again. So eval Docker machine and node1 -- swarm and Docker compose up -d. And you see one line that we didn't really give much attention to earlier, creating network Docker coins default with the default driver. So if I do Docker network ls, in the output, I will see the Docker coins default network using the overlay driver. And I also have a network for the registry. So this is the private network that has been created by Compose for my application. Remember, we can create those networks with Docker network create and so on, and then Docker run --net. But it's way easier to use Compose because it will do that implicitly and will fairly reasonable defaults. So let's check on our application now. That's the address of the web UI. So I'm going to put that into my browser. And fair enough, my app should be running at exactly the same speed as before. Just give it a moment to to initialize, and there we go. So if I want kind of a confirmation that my app is really running across the cluster, if I do docker ps, this will give me, okay, so I'm going to unzoom a little bit, and I do apologize in advance. This is probably unreadable, but if you do that on your own cluster, if you look from a distance, so on the bottom, we have the 5 console containers. Then here we have the 6 containers for the registry, the backend and the 5 front ends. And here we have the 5 containers for the application, RNG, Redis, Worker, WebUI, Hasher. And in front of the name of each container, you can see the node on which it's running. So for instance, Docker Coins Worker, here it says node 5 / Docker Coins Worker. All right, so running the app, getting the graph, scaling. So we can scale just like before. I can do docker compose scale worker equal 10. Just like before, the graph will go up, but only up to 10 hashes per second. Yeah, the network is being really picky, so it's going to be a little bit hard, but trust me, it will settle down to 10 hashes per second. And if I do docker ps, so now I have a bunch of containers, but let's use like less. And I can see like my workers are spread, like worker 7 is on node 4, worker 6 is on node 3, and so on and so on and so on and so on. So at this point, it would be a good idea to find the real cause of the bottleneck. Like, is it really a problem with entropy generation? No, it's not. So here, let's see how we're doing on time. I'm going to fast forward over the benchmark a little bit because it's not super exciting. But what we would do here is that we would stop the workers, and then we would use Apache Bench to run a bunch of requests first sequentially and then in parallel against RNG and Hasher. And what we would discover is that RNG doesn't deal with concurrency at all. Like if I do my request one by one, they all take 100 milliseconds. But if I send a bunch of requests simultaneously, the first one takes 100 milliseconds, the second one takes 200 milliseconds, the third one takes 300 milliseconds, and so on and so on. On the other hand, if I do that with Hasher, it behaves just great. Like if I send 100 requests at the same time, they all take 100 and a little bit something milliseconds. Why? Because the RNG service is using a mono-thread, mono-process, mono-request, like not concurrent at all web server, while the Hasher process is using an asynchronous framework to deal with concurrency. And so when you send a bunch of requests to the Hasher service, it just deals with everything at the same time. When you send a bunch of requests to the RNG service, they are queued sequentially and dealt in order. So that's why when you scale up and up and up, the RNG service at some point can't keep up. So now the question is, why does everything takes 100 milliseconds? Because if you know like how hashing and generating random numbers work, there is no reason for a random number generator to take like 100 milliseconds to generate a little bit of random data. And there is no reason for an SHA hashing algorithm to take 100 milliseconds to hash like 32 bytes of data. So why does it take 100 milliseconds? Because in the code, I've put like sleep 0.1 here and sleep 0.1 here as well. So everything takes 100 milliseconds. So why did I do that? There are a few reasons. First, I wanted to have deterministic performance. So I wanted to make sure that regardless of the actual machines on which you run that, whether it's some cloud instances, whether it's like small cloud instances, big cloud instances, your local machine, a Raspberry Pi, a huge server, it doesn't matter. It will always take 100 milliseconds. So you always get kind of the same graph. That was the first reason. Then the second reason is that the code that we write sleeps all the time anyway. So some of you might think, no, that's not true. I'm not sprinkling sleeps all over my code. Yes, you are, except maybe you're not aware of it, but I suppose that most of your code is doing requests to third-party APIs or to databases. And when you do that, your code sleeps. When you do like read the response from this API backend or read the response from this database query, what you are doing is that you say, I want to read from that socket, but if there is no byte available on that socket, then your process will sleep until something is available. So the only difference between code that sleeps explicitly with like sleep 1 second and code that does like read the response on this network socket, the only difference is that you just get put in a different queue in the kernel, but in both cases, the process ends up in the bucket of processes that are sleeping and should be woken up later once something happens. In the first case, the something happens is this timer went out, so now we need to wake up the process. In the other case is some bytes arrived on the network for this TCP socket, so we should wake up the process so that it can process those bytes. But in both cases, the process ends up sleeping. So now, why do the two services behave differently? Like, why does Hasher handle concurrency nicely, while RNG not at all? It's a deliberate choice. When I wrote them, for RNG, I used the default Flask server, which by default, if you don't do anything, it's like one request at a time, zero concurrency, it doesn't fork, it doesn't do anything. And for Hasher, the one which is in Ruby, I installed Thin, and Thin is it's a Ruby gem, and Sinatra, the Flask equivalent in Ruby, will detect that you have Thin and will be like, okay, I'm going to spin up an asynchronous server. So this is not a Python versus Ruby thing. If I had wanted, I could have used Gunicorn for the Python service, and I could have decided to not use Thin for the Ruby service, and then we would see exactly the opposite result. So how can we make the RNG service faster? The first super easy solution is, well, just comment out sleep in the code, and that's it. Except there are two problems with that. The first one is that in the real world, network latency exists. So you can't just decide to remove the latency that happens when you wait for an API or database to send you the result. And also remember, we had decided to not change the code. So we can't just remove sleep and deal with it. So what we're going to do is that we're going to scale out RNG. We are going to create multiple instances of RNG, put them behind the load balancer, and then we're going to connect to the load balancer instead of connecting to the individual RNG. So we can try to scale directly with Swarm and see what happens. So I can do docker compose scale RNG equal 5. I do that, and then I go to the web graph, and here I could see pretty much anything. So that's like, what? Like in that case, I see nothing. Like it stays at 10 hashes per second and nothing happens. Now, believe it or not, but when I did this at OSCon, it was 2 weeks ago, when we scaled up, the graph went up a little bit, not to something steady, but it kind of made some wave. So why? This is because here we are relying on DNS round robin for load balancing, and that's a super random way of doing things. Why? So let's see here. So if I'm in one of my workers, so for instance, if let's say I do docker exec -ti docker coins worker 1 bash, Interesting. It should boot sh instead of bash. And I do like a ping RNG, and I try multiple times. It always pings 10.003. But if I do ns lookup, it sends me a bunch of backends. If I were to scale down the workers and then scale them back up, maybe something different would happen. Like, you know what, I'm going to Docker Compose scale worker to 15. And as I do that and look on the graph, yeah, now I see the graph coming up, which kind of doesn't make sense. Why would the first 10 containers only send their request always to one RNG backend, and the new instances that I started would spread the load correctly? This is because of the way the resolvers work. Like, the DNS resolver will resolve, get a bunch of IP addresses, and then it might sort those IP addresses, hand them out to the client. In that case, it's the Python code doing the request. And that code can decide to use the first one or randomize them, or it could sort them, or it could sort them according to something in particular. Like there are some resolvers that will kind of hash the output with their own IP addresses. So you can get some really random results, especially because the DNS resolver, it's not something in Python. It's something in the C library. So if you run on a different distro, or if you run with different versions of the libc, or if you are using IPv6, or if you are using multiple resolvers, you could get different behaviors. So TLDR, it depends. Good luck, have fun. And to illustrate that, I'm going to run this little snippet here that's going to resolve 5 times the name RNG on every single worker container and see what we get. So you can see, like, on containers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it always resolved to 10.003. Now let's do that on the 15 containers that they have. And surprise, on containers 11, 12, 13, 14, 15, I get a mix of the different RNG backends. But remember, we are supposed to have 5 RNG backends. If we look at the output here, we only get 16 and 17. Here 16, 17, 19. Here 17, 18, 19, but not 16. And in any case, in all those, we never see 10.003. Doesn't make sense at all. If somebody knows, I'm willing to part from a large amount of really good whiskey or whatever beverage of their choice to really understand how that works. But what we have to learn from this is that we can't rely just on DNS round robin to achieve fair load balancing, because that's not going to work well. So what should we do? Well, we should use a real proper load balancer. So that there is one way would be to, instead of doing Docker Compose scale RNG, we could patch our compose file and put RNG1, RNG2, RNG3, RNG4, and then we would put an RNG service which would load balance across RNG1, 2, 3, 4. That would work, but that wouldn't be super nice because we wouldn't be able to scale with Docker Compose scale, and we would have to change the compose file each time we want to scale up or down. So ideally, what we want to have is that we want our RNG container to be like this scalable backend, but we also want the RNG container to be the load balancer. In other words, and that's, I'm fully aware that it's past 4 p.m. and that you're probably tired at this point, but that's one of the trickiest thing here, is that I want the RNG name to simultaneously be my RNG backend and my RNG load balancer. Because when I'm in my worker code, when I'm connecting to RNG, I want to connect to the load balancer. But when I do Docker Compose scale RNG, I want to scale the backend, not the load balancer. So the solution lies in the fact that the naming of the containers is per network. So what I'm going to do is that RNG will continue to be the backend itself, so that when I do Docker Compose scale RNG, I'm scaling backends. But I'm going to have a RNG LB, that's going to be my RNG load balancer, and it's going to have a network alias of RNG, so that when my worker code connects to RNG, it actually talks to the backend. And I have a couple of diagrams to illustrate that. This is my original Docker Coins application where all 5 services sit on the same network. That's the Docker Coins default network. What I want to have is 3 networks. So there is the default network, that's the white background thing. And then I have the green network and the blue network. So the green network is for the hasher service, and the blue network is for the RNG service. And when I'm in the default network, if I resolve the name RNG, it will be the RNG load balancer. When I'm in the blue network, so the RNG network, now RNG is going to be the bunch of backends that I have here. So we're going to do that manually in the YAML file, and now I think you will see what I meant when I said we're going to do a YAML-defined networking. So let's edit the compose file. So first thing, I want to create an extra network. So networks, RNG. I'm going to just call it RNG. And I'm putting like RNG colon. So it's a key value, but I'm not putting any key and value. It's just like if I wanted to have like extra options, I could put stuff like that if I wanted, but I don't want any option. I just want to declare we have an RNG network. Then I'm going to put the RNG container in this network. So networks RNG. And again, it's RNG colon to indicate that I might have options here if I wanted. And then I create the RNG load balancer. So the RNG load balancer is going to sit both on the RNG network, but also on the default network. And in the default network, it's going to have the alias RNG. And the RNG load balancer is going to use the jpetazzo hemba image. And I'm going to give it a special command. I'm going to give the command run. So for the hemba image, the hemba image supports dynamic reconfiguration. And so here, what I'm telling it is, you should just start and wait for a configuration file. So the app will start, the load balancer will be in a broken state, and then we will inject the configuration. Okay, let's double check on my slides that I didn't forget anything. All right, we place RNG on its own network. Then I put the load balancer both in RNG and default networks. And then I put the initial setup for the load balancer. Okay, now I can bring up this application. So Docker Compose up-d. So it's creating the RNG network. It's recreating the RNG container because now it's on a different network. It's creating the load balancer, and then it's recreating the 5 RNG containers. So that's going to take 10 seconds per container. Because remember, when you stop a container, it tries to use the polite way. It sends the term signal. But if the container ignores that signal, then after 10 seconds, Docker is like, oh, you're still running. Well, I'm going just to send you the kill signal then. And when I wrote the services, I kind of deliberately didn't do any kind of signal handling. And so that's why it takes 10 seconds per container. And by the way, here it's using a rolling deploy strategy. It's restarting each instance one by one to make sure that you don't like kill everything and restart everything in one step. Okay, if I look at like Docker Compose logs --tail, let's say 10 --follow worker. I see a bunch of errors because the workers are connecting to the RNG load balancer, but the RNG load balancer is not set up at this point, so that fails. So I have to inject the initial configuration in my load balancer. So that's how we do it. So what is this weird command here? So I'm doing docker run. Let me put that on top of the screen and a little bit bigger font. So docker run. So I'm running an HMBA container. And the HMBA container also comes with a special mode, which is reconfigure. In reconfigure mode, is just generating the new configuration file and saving it to disk. And then it exits. So how is this container going to actually reconfigure the other load balancer? The answer lies in this -- volumes from option. The configuration of the load balancer is in the volume. So when I use volumes from, this container will generate a new configuration file, write it in the volume, which happens to be shared with the load balancer. The load balancer is currently watching on disk, like for this configuration file to show up. And so as soon as the config file is there, then it will pass the config file, and if it's valid, then it will start a proxy. I have another option here, --net container docker const rng lb1. Why do I have that? Because I need the names to resolve exactly as they would for the load balancer. Because when I generate the configuration, I also validate the configuration. What is my configuration? My configuration is listen to port 80 and load balance traffic on docker const rng1 port 80. So I need docker const rng1 to resolve correctly, and the only way to achieve that is to be exactly in the same network as the load balancer. So I just do that. It says configuration file is valid, and that's it. Like now, if I do like docker compose, what am I doing? What? Stop. Help. Docker compose. I'm not typing the right characters or what? Docker compose logs rnglb. Can I do like, I think it's -t for timestamps? Yeah. If we look on the timestamps, we can see like starting main loop. So it started like at some point, and 3 minutes later, that's when we generated the config file, and so the load balancer say, I found the chip proxy, the config is valid, and I can load it, and so on and so on. And here, in the output, I can see, all right, so the big gap here is when I switched to the load balancer thing, but the load balancer was not set up yet, so for quite a while, my workers were not functioning correctly. And now everything works fine, except the load balancer is set up to send all the traffic to one machine. So now I'm going to reconfigure the load balancer. And so I'm just going to put all the addresses of all the backends. Docker const rng3, Docker const rng4, and Docker const rng5. That's it. And here, almost instantly, the graph goes up. And this time, the load is correctly spread across all the backends. You can see that we have a throughput which is way higher than what we had when we had this kind of half-broken DNS round-robin thing earlier.
The volume, the specification of the volume for the HA proxy, that came from the Docker image that had the
Yes, the fact that the load balancer is picking up the configuration from a volume comes from the definition of that image. If we look into the Docker file for jpetazzo/hamba, we would see like volume / something. I can't remember exactly which path it is. And so that's how it works. So what is interesting now is I can scale up and down, and after scaling up and down, I just have to run like one command to update the config of the load balancer. So that's, I mean, it's not bad, but that's still kind of a lot of work in the sense that you have to patch this YAML file, and then you have to run this an extra step to adjust the load balancer configuration. Can we automate that? Yes. So we are going to use DNS to discover the addresses of all the backends. Because remember, you can do NSLOOKUP RNG, and it will give you the IP addresses of all the RNG backends. So we can totally use that in the load balancer so that the load balancer can infer automatically, without running an extra step, the addresses of the backends. And to automate that, so here I have an extra container called watch.dns. So what it does is pretty simple. It continuously resolves the same name again and again. So in that case, it resolves RNG, like every second. And it compares the set of IP addresses that it gets. And whenever that set changes, it's like, oh, you just scaled up or down. Well, something happened. We need to update the load balancer configuration. And it will automatically generate a new load balancer configuration and write it, and that's it. It's pure POSIX shell at this, just because that was easier in that case, and I wanted to reuse parts of what I used for the other thing, and it's less than 100 lines. And so we could definitely have something nicer and even smaller in Python or Go or something like that, but I wanted to have something that remains readable for everybody, basically. And if you look at this, it's like almost half of the file is for HA proxy configuration templates, and the other half is to actually watch those DNS records and react when they change. Okay, so now how do we use that? I also have a script that will automatically add not only the load balancer, but also the custom network and this watch DNS thing for you. Because if you keep in mind the big picture, each time I want to deploy, I have to run build tag push. It generates me a new compose file, and then I have to do manual edits in this compose file? No way. We are going to automate those edits. So I'm going to restore my compose file to whatever it was before adding the load balancer. So I'm removing the custom network, I'm removing the load balancer. Yep, I'm back to the straight output of build tag push. And now I call add load balancer v2 on RNG. And if I look at my compose file again, automatically it added the RNG network. It put RNG on its own network. It created RNG-LB. It's doing a couple of extra fancy things, like it gives an alias to the RNG backend so that we don't have to use the command run for the load balancer. Because remember, when I started the app the first time, the load balancer had 0 configuration, so the app was not functional. I don't want that. I want the app to come up without me having to do a manual operation. Then I have RNG-LB. And finally, I have RNG-WD, so the thing that watches DNS. And it's also using the Petazzoni watch DNS image. It's also the RNG network. And it has volumes from RNG-LB. And so what it will do is generate load balancer configurations. Those load balancer configurations will be automatically picked up by the load balancer. Let's try to bring that up. Docker compose. You know what? I'm going to scale back. No, so scale worker equal 1, RNG equal 1. And then I will bring up that new compose file. So Docker compose up-d. So it's like, okay, you have the new watch DNS thing, so we're pulling the image everywhere. Then it's recreating the containers that are now on different networks and need to be updated. And if I look at the web UI, it's going back to like to the initial scale thing we had, like 3.333 hashes per second. Now the big difference is that, look, I can do Docker compose. Okay, I'm going to split the screen so we can see the logs as I'm working on stuff. So let's split that like that. And then in the bottom part, I'm going to do Docker compose logs. I want RNG, so the -- follow RNG LB and RNG WD. Okay, so first, Docker compose scale worker equal 10. So I'm adding new workers, but remember, I only have one RNG backend. So if I look on my graph here, yes, it went up, but it's capped at 10 hashes per second because RNG is my bottleneck. Now I'm going to scale RNG, Docker compose scale RNG equal 2. And below, you will see like, wow, that I need to have more output in this thing. How can I scroll up? Damn, maybe if I unzoom a little bit. Yes. You can see the WD, watch DNS. It did notice that the list of IP addresses for RNGBE changed from this to this. I now have two backends. So it created a new configuration for the load balancer and dropped that configuration in the volume, which is shared with RNGLB. RNGLB almost instantly noticed, oh, there is a new HAProxy configuration. So we validate it, and if everything is fine, we restart HAProxy with the new configuration. And in the graph, I went from 10 hashes per second to 20 hashes per second. And of course, I can scale further up. So on top, I'm going to scale RNG to 3. And almost instantly, in the bottom window, we see, OK, change from 2 backends to 3 backends. And here now I'm at like 30-ish. And we can be a little bit more aggressive here, like worker equal 40 and RNG equal 10. And let's see what happens. So while this is working, I'll do some comments on this strategy. One of the kind of frequently asked features in Swarm is, hey, can we fully automate that? Like, can we completely out of the box, if I do Docker compose scale, I want the load balancer to be added, and I want all this thing to happen without me using those scripts and so on and so on. You can see the output here is much, much higher. Great. This is something that we are building into the next releases of Swarm, but we also want to keep the possibility of doing whatever you want with load balancing. Because at first, people say, OK, just give me built-in load balancing, because this is like super complicated, and what should I do with that? Now, if you ask, OK, what kind of load balancing do you want? Do you want round robin? Do you want list connection? Do you want something based on back pressure from the containers or the nodes running the backends? Do you want something that monitors the average response time and sends the request to the backends that have the best response time? Generally, people kind of stop, sit back a little bit, and think, I don't know, what's the default? What do people do usually? Well, the answer is it depends. Sometimes you want to do pure round robin because it's simple and it just works. Sometimes you want to do list connection because, especially if you're using Python or PHP or Ruby, And for each connection, you need a backend up and running. So you want to keep the connections as much like balanced as possible. Sometimes you want to send to the backends that have the best response time, but that only makes sense when the response time is kind of homogeneous across requests. Like if your application has some requests that take 10 milliseconds, but some requests that take 3 seconds, whenever there is one request that takes 3 seconds, the load balancer will be like, oh, this backend is super loaded, I should send the request elsewhere. No, that doesn't make sense. Sometimes you want session affinity, which means that when the same client connects over and over, you want to send him always to the same backend because the backend has some local state or some cache, and so it's just faster if the same backend serves the request for a given client. But then the load balancer needs to be aware of that. So typically you will want to use cookie stickiness, which is something where the first time a client shows up, you send him a cookie that says, your backend will be this. And that way, when the same client connects over and over, you can use that cookie to route the client to the right backend. All those things, they don't come up automatically. You have to decide, you have to set some options. Some of those things are implemented beautifully in HAProxy. Some of those things are implemented in Nginx, but not in HAProxy. Some of those things for crazy high loads will be not in HAProxy and Nginx, but you will want something like IPVS, which is kernel side. Sometimes you will just want to have a hardware load balancer for reasons, et cetera, et cetera. So for this reason, our priority when rolling out Swarm was, okay, we want to give you a way to do whatever kind of load balancing you want, because on real-world deployments, that's what people want. It's like, oh, I don't want load balancing just to tick a box in the list of features. I want load balancing because I have specific needs, and if I don't pick the right load balancing strategy, at some point I will run into problems. So that's why first thing was to give you a way to implement any kind of load balancing, and in future versions of Swarm, we want to kind of bundle the most frequent methods into Swarm itself and give some sensible defaults. All right, where am I in the slides? Okay. So if we recap, we have this pipeline where I have this build tag push script that will create build artifacts of my application. Then I feed that into the add load balancer that will automatically add the load balancers and the DNS watchers. And what I would like to show is just like one excerpt from that chapter about logging. So I'm going to start an Elasticsearch cluster. So let's scale back first. RNG equal 1, Walker equal 1. Unset compose file. So I go to my ELKey directory here. I have a Docker Compose YAML file that defines an Elasticsearch container, a Logstash container, and a Kibana container. If you're not familiar with ELK, Elasticsearch is a JSON store, so we will store documents in it, and by documents I mean log lines. Each log line will be a tiny document. Kibana is a web UI to visualize that, and Logstash is a kind of pipeline that will accept logs using the GLF protocol and then store them into Elasticsearch. And you're going to see, so I think we're kind of out of time, but I want to show you in like, let's say, 2 or 3 minutes how we can have this logging pipeline up and running. And so what we're going to do is that we're going to have this Elasticsearch cluster. I'm going to have a Logstash container running on every single node, so that on each node, I can send my logs using the GLF protocol on a local address, and that will be like accepted by Logstash, and then Logstash will route that log line towards Elasticsearch. So now I do for n in 2, 3, 4, 5, do Docker compose scale Logstash equal $and done. So it's the same trick as what I used earlier for the registry front end, where I want to end up with one front end on each node. Here I want one log stash on each node. Then I want to know, okay, where is the Kibana web UI? Port Kibana 80. There we go. 5601. And while Kibana is loading, I will transform my compose file once again so that now I add logging. By default, the output of the containers is received by Docker, and Docker stores that in local files. But I can change that, and I can tell Docker, hey, I want you to send the logs of this container using the GLF protocol over something else. So I just do like add logging, and add logging is pretty simple too. I'm just going to show the output. It's taking every service, and it's adding this little logging section. It says use the GLF driver and send the logs to UDP localhost 12201. 12201 is the default port for GLF. And I'm adding that to every single container. Now I do docker compose up-d again. And this time it has to recreate all the containers. And so if I look into Kibana here, what's going on here? What am I supposed to pick here? Oh yeah, I have to go to Discover. And here I see my container logs. I don't know if you recognize this output, but I can, let me just make that a little bit cleaner. I'm going to select the fields I want to see here. So I want to see the host, I want to see the container name, and I want to see the message. And so in host, I will see like node 2, node 4, node whatever. I see the name of the container, and then I see the log line. So you could see like in a few minutes, I just spun up an ELK cluster. I reconfigure my app to send the logs to this ELK cluster, and I can visualize those logs with Kibana. And so my pipeline now becomes build tag push, then add load balancers, then add logging. But all that can be executed like in sequence without any manual operation. So that kind of wraps up what I wanted to show. So I had to kind of squeeze the ops section, but the content is there, and this is still available here. If you had the specific questions about like some of the sections I had to skip in the ops chapter, feel free to come and talk to me afterwards. Thanks a lot. Let's see why I want to jump to the conclusions. Okay. So what haven't we not covered? We haven't covered like system metrics, like how do I keep track of the CPU, memory usage of each container and of each machine. For low-level per-node metrics, you can continue to use whatever you used before, CloudWatch, CollectD, stuff like that. For per containers metric, it's kind of a new field, and so there is no best practice or best solution yet. You can look at stuff like cAdvisor, Snap, Prometheus. For application metrics and supervision, just continue to use whatever you used before, because that doesn't change. When you're monitoring the uptime of an app in a container, it's exactly just like monitoring the uptime of an app on a VM or on a physical machine. When you want to know if a web server is up, you don't care about whether the web server is in a container, VM, or physical machine. We haven't seen like how to store credentials and that kind of stuff. There is a part about that in the high availability chapter about explaining how you can store those files in console. And if there are other parts that you think are important and should be covered, please let me know, because this is living material. It it is significantly updated at least once a month, and there are minor updates between every single workshop. So I'll be more than happy to add content, and the content is public. So if your favorite feature is missing, you can ask for it, and in a few months it will be there and available on the repo. Conclusions. Swarm changes really fast, so you can expect to see new features, especially in load balancing and high availability in the coming months. And that's pretty much it. Look, about overall complexity, I'm well aware that the pipeline that I show here might appear to be complex. Like, okay, we're running multiple scripts and we're transforming the compose file. So when you're totally new to this, I know that it might seem overwhelming and complicated. But if you revisit this, all the scripts that I use here are less than 100 lines. It's either Shell or Python, so it's really easy to reproduce that and to kind of own that pipeline. So once you're more familiar with Compose and with Swarm and you revisit that, it's like, okay, that's really easy. And if you think about, oh, maybe I want to use that other system that will automate that for me, like maybe I want to use like CloudFormation to describe a template for my application. Well, a CloudFormation template for an app like my demo app here is definitely more than 100 lines. And the best indicator of complexity is that the scripts that we use to deploy the VMs that we use for the workshops are way bigger than the scripts that we use to deploy the Docker Coins demo app on Swarm and scale it. All right, thank you. If you have a few questions, we can do that. Although I'm going to stay a little bit if people have more deeper questions. And if you've been happy with that tutorial, I invite you to fill the survey form. If you've been unhappy, don't fill the survey form. That's okay. Thank you so much.